we can start with Ho Kim, who will talk about sources of the Atlantic water biases in CSM2.
Okay. Can online hear me well? Maybe no one there. Good morning. Sorry to start off the meeting with the bad things about model. Yeah, so this is about Arctic Atlantic water biases in CSM2. So I'm using CSM2 pop only, but at the end I'm going to show this is still bias is still there in MOM. So please be interesting. So relatively warm salty Atlantic water flow northward through Jinsey along the Norwegian currents. About half of it enter the Arctic Ocean through Frem Strait, another half enter Arctic Ocean through Barents Sea. Maybe I'll just use, yeah, Barents Sea opening here. So the Frem Strait branch sinks under the fresh surface layer. So the sea ice and fresh water kind of shields the Atlantic water from the air sea interaction. So it's relatively warm and saltier. But this Barents Sea branch experienced air sea interaction before it entered through the St. Anna Trough here and other trough and channels as well. So it's relatively cold and fresh. After St. Anna, the Barents Sea branch joined the Frem Strait branch, then the Atlantic water layer circulate entire Arctic Ocean along the slope. And Atlantic water generally referred to as the water temperature greater than 0 degrees Celsius. The right plot shows the Eurasian Basin average temperature profile from WOA 13. You can see well-defined warm core of Atlantic water layer here, which is about 700 meter thick, and the maximum temperature at the around 250 meter. So the ocean model is having a hard time to simulate this Atlantic water layer correctly. It's generally too deep and thick, so the cold anomaly develop around the observed core and the warm bias below it. So it's been there for many decades, but as you can see from this example, the same bias still exists in forced JR55 forced OMIP2 simulations. So the dashed is hard to see, but dashed black line is the multi-model mean, and black is W observation basically. This is the spatial pattern of the bias at the observed core around 300 or 400 meter. So you can see about 1 degree cold bias in the Eurasian Basin in terms of multi-model mean. The situation is similar in couple simulation. The blue line here is the multi-model mean, and black and green line is observation here. So again, you can see thicker, deeper Atlantic water layer. And yeah, there is also fresh bias in the Atlantic water layer, but this is not the focus of this talk here. I want to make one thing clear here. So we can separate this bias into short-term and long-term biases. Of course, short-term biases generated locally within a decade or so, and long-term bias is drift. So it's moving slowly over hundreds of years to another state. So this is example of CSM2 here. Blue line is the new kind of PI control simulation we ran for this study, starting from WOA 13 initial condition. So within a decade or so, we got this cold bias in the Atlantic water layer, but one bias is not very severe in the deep ocean. And red line shows this, the CSM2 temperature profile from CMIP6 PI control, which has been run for thousands of years. So over time, we have this very warm bias in the deep ocean. So in this talk, I'm focusing on short-term bias, not this long-term bias here. This Atlantic water bias can be generated by many things. Yeah, of course, it can be generated by biased Atlantic water inflow from the Jin-Sea to through Fram Strait and Barents Sea opening. The biases can be generated also incorrect water mass transformation due to either surface fluxes and or mixing over the shallow shelf of Barents Sea and Kara Sea, and or mixing with ambient water within the troughs and channels, Sayaneta Trough mostly, but also in other channels like Victoria channels here. The bias can also be generated inaccurate misrepresented horizontal and vertical mixing in the interior or slope region. So previous study touched few of these possible potential sources before, but no study systematically examined the potential sources using a single model. And this is what we have done in this study. So to do so, we use multiple configuration of CSM2, both low-res and high-res configuration, force configuration of CSM2, as well as low-res configuration of CSM, couple configuration of CSM2. So we first ran many sensitivity experiments using low-res configuration of forced low-res configuration, which can be grouped into three types: interior TNS restoring experiments, mixing parameter experiments, or combinations of both. And then we ran selected experiments using high-res force configuration and couple configuration. For force simulation, we used 2003-2004 repeat year forcing, starting from WOA 13 initial conditions. We use this 03-04 repeat year forcing because we have already 03-04 high-res control simulation, so we want to leverage the simulation, but doesn't really matter. Similar bias appear whether IIF or different years of RYF are used. I mentioned that we had to run new PI control starting from WOA 13 to clean comparison. Yeah, and our simulation run for 30 years, and last 5 year average. I used last 5-year average to examine biases, focusing on the temperature and circulation in the Eurasian basin. So let's first look at the bias in the control simulation. The blue line is low-res forced, red line is high-res forced, and yellow line is couple simulation. Yeah, you can see the same bias as in other model, the deeper core, thicker Atlantic water layer, which is deepest in surprisingly high-res simulation and thickest in high-res simulation. Because of so as a result, there's a cold bias at the observed core, Atlantic water core, and the bottom panel shows the spatial pattern of bias, cold bias at the observed core, about 300 meters. which shows substantial bias in the Eurasian basin. And I want to briefly mention that this bias initially developing quickly within a year along the slope, because later I'm going to show the restoring experiment where this slope region is temperature and salinity restored in this slope region in the Eurasian basin. So let's start with restoring experiment. So first experiment, I restore temperature salinity in the Jin-Sea from second layer to the bottom. Surprisingly, the entire saline water is layer in the interior Eurasian basin is gone. That's because, well, this is special pattern, so we have more cooling in the Western Eurasian basin. And this shows the vectors and the speed of velocity at 300 meter. I'm showing here kind of reanalysis estimate or from ORIAS-5. Yeah, it's very weak in control simulation already, but with this restoring, the circulation becomes even weaker. Fram Strait, north of Fram Strait, north of Svalbard, and the entire circulation then becomes anticyclonic instead of cyclonic. I want to mention that the inflow from St. Anna Trough is cold bias in both low rest control and Jin-Sea experiment. So because of the anticyclonic circulation with Jin-Sea restoring and weaker circulation from Fram Strait, so cold bias gets worse in the Western Eurasian basin. The next, we perform restoring experiment, the Barents and Karasik restoring experiment from the second layer to the bottom or 500 meter. It's slightly better, so at least we have temperature slightly warmer than 0 degrees Celsius in the Atlantic layer, but much colder than control simulation. The cold bias got worse in the Eastern Eurasian basin. The circulation east of St. Anna Trough is a bit stronger, but the bias in the St. Anna Trough is still there, so the more cold bias water gets back into Eurasian basin. That's why I see more cold bias in the Eastern Eurasian basin. So getting right over the shelf is not enough. And then next, we restored temperature and salinity in limited region at the exit of troughs and channels. Then boom, yeah, we got warmer and shallower core and colder deep ocean, which match observation much better than the control simulation. The special pattern. The bias is reduced mostly in the Eastern Eurasian basin, and you can see substantially enhanced circulation east of St. Anna Trough, which flows along the Lomonosov Leach. Then there's a recirculation going on from that branch. So I think because of the enhanced circulation brings corrected source water from St. Anna Trough, that kind of removes the cold bias in the Eastern Eurasian basin. So this suggests the importance of inflow from the troughs, not just St. Anna Trough, but other troughs and channels, simulating the properties and circulation of the Atlantic water layer. Yeah, I just mentioned that other seems other channels also important because the circulation in the Western Eurasian basin is also enhanced with this restoring. So next experiment, we did the restoring along the slope region between 500 meter to 2,000 meter. Now we have almost matching perfectly observation Atlantic water layer. Yeah, most of biases in the eastern Eurasian basin is gone. Yeah, circulation is still stronger, but here in this experiment, the circulation doesn't really matter because we restore the temperature and salinity along the slope. But we can confirm that that the biases, these cold biases, originate from this slope region. Let's moving on to mixing experiment. So in this experiment, we reduced the vertical background mixing about an order. Then we got shallower core, which is good, but the Atlantic water layer becomes much colder. Yeah, the circulation looks very similar. And next experiment, we perform scaled GM experiment. So here, the kappa Piconal and the thickness coefficient scaled by the normalized grid cell area. So smaller kappa in the high latitude Arctic Ocean. Then we have very over a warm Atlantic water layer. That's because the circulation in the western Eurasian basin becomes stronger. But it's still big in the eastern Eurasian basin. But the problem is then the more heat, warm biased water entering through firm strait, thus we have a very warm Atlantic water layer, especially in the deep ocean here. Then we combine a few of this experiment, especially weaker vertical mixing, scale GM and trough restoring. Before that, I'm gonna mention that the yellow line shows the combination of weak vertical mixing and scale GM case. It's still more like a scale GM, but the core is slightly shallower than the GM experiment itself. The purple line shows the combination of these three, shallower and warmer Atlantic water core. Then the GM case, and also cold, the deep ocean becomes colder. The stronger circulation is there, and because of trough restoring, we have this strong circulation in the eastern Eurasian basin. So that's why we see the reduced bias in the eastern Eurasian basin. Let's move on to HIRAS. We did two experiments, weak vertical mixing and trough restoring. As you can see from this profile, unlike low-res, the weak vertical mixing doesn't make much difference. So we stop at year 15. Let's move on to trough restoring. Consistent with low-res experiment, we have warmer, shallower Atlantic water layer with colder deep ocean, matching observation really well. Same special pattern at the observed core and circulation pattern. So this blob of cold bias is gone with magically just restoring small areas in few channels and troughs. Again, the circulation in the Eastern Eurasian basin becomes much stronger along the Lomonosov Ridge especially. And recirculation kind of appears they suppress this cold bias in the interior. So it's kind of boring to show the similar plot again and again. So I'm going to just show this profile for a couple experiment. Yeah, as low res force, high res force, similar improvement is obtained. We have slightly warmer core with trough restoring, but much reduced warm bias in the deep ocean. When we add Wick-Barker mixing and scale GM, we got even warmer Atlantic water layer with a shallower core. So this kind of supporting the important lower trough and tuning mixing things. So this is key points I want to make. So we found important lower of inflow from the troughs and other channels in setting up the hydrographic properties and circulation of the Atlantic water, especially in the Eastern Basin. So Atlantic water bias is substantially reduced. We have now warmer, shallower, and thinner Atlantic water layer with the trough restoring. So this finding calls for the development of overflow parameterization, like Denmark Strait in CSM2, and even in high res. Also, our study kind of suggested tuning of this mixing parameter can improve the Atlantic water property and circulation too. It's more relevant to low res. We show that scaling GM diffusivity coefficient degree the area substantially strengthened the circulation in the Western Eurasian Basin, but flow pattern is less organized, it's noisy. So I think there's a room for tuning there. One of the problem is if the circulation gets stronger, then the bias in the Jinsea more matter. So we have one bias in the Jinsea. So with the strong circulation, that one bias enters the Arctic Ocean. So we have to then deal with Jinsea bias, not just Arctic bias. This is my last slide, as I mentioned earlier. So thanks to Gustavo, I got the latest simulation with MOM, forced couple case blue and red. Yeah, similar bias still exist with MOM, so we have to think about tuning and putting parameterization to improve this bias in the Arctic Ocean. That's it.
We have time for questions.
Thanks, Hu. That's a cool set of experiments. I was wondering, because the relaxation is non-conservative, do you know that it's enough, to have an overflow parameterization that might kind of reorganize existing water masses and temperature? Or do you think the relaxation is actually inputting a net heating or cooling to the upstream water mass? Does that make sense?
Can you repeat the question again?
It seemed like it was very effective to relax in this kind of boundary region, and so you attributed that to these overflows and stuff. But then I guess, and then the suggestion is that, well, maybe how we handle overflows could improve the sharpness of this water mass. But also the relaxation, if I understand correctly, is non-conservative, right? So you are adding or subtracting heat in this particular profile. So do you have the heat upstream of those overflow areas such that you could reorganize it, or do you still need to introduce or take away heat from the system?
Yeah, I haven't think about that way, but I think the current overflow parameterization is conservative, I believe. So if you just apply the same technique to this parameterization, then it's not adding any heat or thing I'm not, yeah, I don't know.
Yeah, guess you could try it, yeah.
It's sort of a follow-up to this. I mean, another approach to sort of get at that question would be to do, rather than restoring temperature and salinity directly, is use the semi-prognostic restoring of the velocity field, which I know we've used in the past, and see whether changing the flow field without putting in a net heat source. Get at this question, whether it's the transport properties or the water mass origin that's leading to the bias.
Okay.
Follow up? Yeah, and follow up on that. I mean, the issue with that is that we used the semi-prognostic method before, and usually you have to apply it away from topography or you get into trouble. And so science, like right now, what you're showing is like it's close to topography that you need to apply the restoring. It may be challenging to do that. Just
Follow up with analysis. So 2 questions about this comparison here. First, have you looked at the diapicnal diffusivity in the MOM configuration you're using, and does it fit more on the higher or the lower end of the diffusivity that you're seeing in POP? If it's something borrowed from GFDL, we had been using way too much mixing in the Arctic. Maybe somebody here at NCAR was clever enough to spot that and fix that, but it might be that that's one of the commonalities.
Okay, yeah.
And then the second question, with the hybrid coordinate, MOM could be either in a quasi-isopycnal coordinate or a Z coordinate. And the critical depth range in the troughs here, is it a Z coordinate model?
It's hybrid, icon, yeah.
Yeah, but I think it's basically Z star in the entire Arctic. Even in the hybrid coordinates become Z star in the Arctic. Mostly, right? Right.
At those depths, I think it's probably these are,
Okay.
yeah.
Okay.
So we heard last September from Andy Hogg about an adaptive coordinate that would help us to kind of stay more isopycnal even at higher latitudes. So I agree this is something we have to pay close attention to, but Andy's ideas about an adaptive vertical coordinate might also be a good thing to look at. And secondly, you've made a really compelling case that reducing the diffusivity helps the signal not to get diffused out. I suspect the same might apply to the MOM case you're looking at here as well.
So follow up. Was it the background mixing that you reduced?
Yeah, we had this Henye background mixing, which is based on a profile from the Pacific Ocean, and we just kept as a function of latitude, we just kept extrapolating into the Arctic. And that was a bad idea because internal waves don't propagate in the Arctic. You're past critical latitudes and it's a microtidal environment. There are all sorts of reasons why observations from the Pacific should not be used to calibrate the Arctic.
Alice.
Not having, I know that like the Denmark Strait parameterization, overflow parameterization exists, and there's something similar in Antarctica, I think. But what would the level, do you know what the level of effort would be required to extend that to like some of these basins here? Is it a huge amount of work or is it relatively transferable?
That's a very good question that I don't know. Well, I guess.
yes, the short answer is no.
Yeah. We need to talk to is the one that
Okay.
implemented parameterization.
Yeah.
Following up on that, we've dealt with some overflow. We've improved some overflow properties by editing topography in other places like the Greenland Scotland Ridge. Have you edited any of those? So that would be easier than trying to put a whole new parameterization in or tuning up a whole new parameterization. We might try that.
I didn't mention here in my talk, but I did kind of experiment with modified topography. Surprisingly, the bias is robust. I think it's still there. Maybe I did wrong. I haven't. It looks pretty much same, even if I stiffen the slope or deepen the well, not Santa Ana trough, but when I kind of deepens the French Strait, the bias at the French Strait remains about the same.
Right. I haven't done those things myself.
Do you have any questions online?
I do.
Go ahead.
Hi. So I missed some part of it. One of the issue about the overflow at the San Andreas Trough is it's big in the Sverdrup. Basically, if I remember correctly, when we did the Core 2 paper, it was almost 1 Sverdrup, which is the same order of magnitude of the Mediterranean overflow. When you do the relaxation, did you guys try the Barents Sea, the shallow Barents Sea DNS rather than the shelf, but just to control the Barents Sea's water properties?
Yes, well, not just Bering Strait, but we did a restoring experiment where the upper ocean in kind of Bering Strait side, Arctic Ocean is restored to control the fresh bias there. But yeah, didn't make much impact on Atlantic water.
The Bering or Barents Sea? Sorry.
Oh, yes. Oh, so I have restoring experiment over the Barents and Kara Sea. Yeah,
And that didn't change?
make it worse.
Okay. Yeah. And for the Bob's argument, yeah, the default HiCom is his star in the Arctic. I have a regional model, which I will show tomorrow. It looks like that, basically, full Z.
Okay, if there's no more questions for who, let's take it one more time.
Okay, well, morning everybody, and thanks for the opportunity to give that update on the Mesa Clip project. So Mesa Clip is a collaborative effort between Texas A&M and NCAR, and you have like the cast of character listed here. And essentially that's the project that is funded by NSF that we use to explore using like finer resolution for climate model. And so by high resolution, what we mean is like essentially an leading model, so 1/10 of a degree. And what I usually refer to like TC permitting atmospheric resolution, so 1/4 degree atmosphere. Just to give you an idea of what it's looked like, we have this like very cool animation that was made by the Viz Lab at NCAR, and Matt was instrumental in that. And it's showing the specific humidity in 3D, and later on you will see like we are zooming in, and you will see like induced total rain precipitation over land. And during the second part of the animation, you will also see like TC cold wake in land and rain essentially associated with TC when they make landfall. So as part of that project, we have now been able to run like several thousand years of high-res CESM climate simulation. And I try to list like most of them here. The one that are in green are the one that have been already released to the community. And usually we just go with like the CSM management plan and release the simulation as soon as we have a paper documenting them. So we have like a 500-year PI control. We have like a 1% CO2 and 4x CO2. We have like a 10-member ensemble of historical that you can branch into like 10-member RCP 85 or RCP 60. And then we have single member of like different like RCPs with like weaker warming. We also did some experiment where we constrained the ozone to remain like at pre-industrial level. We have like AMIP simulation. We did all the high-res MIP experiment protocol as part of that. And we have 5 cycles of like 4th ocean simulation that I think will use maybe some of that, I forgot. We also have like decadal prediction experiments. So that's no like a fully coupled model that we integrate like a few years out. And we initialize that from like observation or in our case, like the 4th ocean simulation. This one is in light gray because some of the simulation are available The one that we're using, Steve, 2023 paper have been made available essentially, but we are extending that set to include every year initialization in May, September, September. And we have a lot of like corresponding low-res simulation using the same dicole, but just like finer resolution, coarser resolution, so like 1 degree in all components, so the kind of CSM workhorse configuration. So if you want to learn more about all this data set, you can go, we have a website where we try to keep like up to date and including like link to the how to access the data. So all the data is now served through the resource data archive. So it's a very nice framework where you can essentially access the data locally on our system. If you have access to our system, and you can use Casper to analyze the data, or you can download the data remotely through Globus or HTTPS. And CISL is actually helping us to also like create the Intech EDSM catalog for that, so that will really help like make the data as usable as possible. They are also working on like a way to optimize the I/O, so because it's a huge amount of data. I mean, I think the total amount is like 5-6 petabytes. So just like working with the data is a challenge, and so we are getting help from CISL to make the data as usable as possible. One thing that we recently added, thanks to Adam Phillips, is like the CVDP diagnostic for all those simulations. So you can go on the website and you can get a sense of what the climate look like when you move to this like finer resolution. So this is just an example of like the type of plot that you can get. That's like the winter precipitation trend during the observational period. You have like on top, you have the high-res 10-member ensemble, and then the low-res 10-member equivalent. So this is using the same dicole, and CSM1 lens is kind of the state-of-the-art for the nominal 1 degree resolution. So we added that also, and you can even get like all the individual ensemble member. You may need like ChatGPT to help you with interpreting that, but that's available here. So yeah, that was Adam was really helpful. Like first like designing that amazing diagnostic package, and then helping us like run it on our data set, which was also a challenge. So now I would like to just like give you some quick highlights of like what we found essentially like moving to high-res. So one thing that we were not expecting is that with the high-res, we are getting much more realistic trend in like the South Ocean. So the low-res, which I'll show like on the top left here, are notorious for not being able to capture this like cooling trend in the South Ocean and also the tropical Eastern Pacific. So the observation of the next plot in I handpicked like one member, member 10, which is strikingly similar to the observation. But if you can see that essentially all the member from the high-res 10 ensemble show some level of cooling, or at least muted warming in the tropical Pacific, which is not the case when you look at the low-res. In the low-res, like you have a very few member that show muted warming, but on average, like it's showing warming all over, which was something that we didn't necessarily expect it. That was a pleasant surprise. So we are exploring, like trying to understand why that we see that in the high-res, and right now our hypothesis is that it's coming from the ocean side. So I'm not showing it, but with the HAMIP simulation, essentially when you go to high-res, you see the same response. So you have like an increase of like wind over the Southern Ocean. So it's not, it doesn't look like the atmospheric, the improved resolution on the atmospheric side only is able to drive that. But if you go to the ocean side, so now on the right, I'm showing post-ocean simulation. So not surprisingly, post-ocean simulation, you bake in the trend. So even at low res, the middle panel, you see cooling. But what you see, the lower panels show the difference. So even if like we use the same forcing, we have like more cooling in the south when we move to eddy resolving simulation. And we can show that it's actually mostly coming from the eddy heat transport pole world. So I'm showing like the low res and high res panel, and as you can see, the total heat transport, so the black line on the upper panel, is like much stronger in the low res, so about twice as much. And most of that is actually coming from the AD component, the blue line. The red line is showing like about the same magnitude. So we are exploring that more thoroughly now, and we have a proposal to look at that more specifically, but hopefully we'll get funded. So stay tuned on that. The lower panels show like trend over the observational period, and you can see that the trend are also very different between high res and low res. So that's another aspect. And this better like trend and tend to improve like the skill when we move to decadal prediction experiment in the high res. So another aspect that is vastly improved in the high res is like tropical cyclone TCs. So here I'm showing like the observation. So it's all the TC that were like observed over the 1950 to 2015 period. The middle panel show the high res, and the panel on the right is the low res. So as you can see, the TC count is much more realistic. It's actually even a little bit too high in the high res. We still have a hard time to get like Cat 5 TCs in the high res, which is expected that with like only 25 kilometer resolution, we'll need to go even farther than that to get this very strong cyclone. But like, so essentially, yeah, we do get like a much more realistic representation of TC in the high res. And so now we can look at like future projection. And this is now looking at the difference between the late 21st century TC occurrence minus like the kind of present day, so 1950 to 1980. And interestingly, you can see that the number of TC, especially in the Atlantic, is going down. So there is less cyclone, tropical cyclone, every year in the future warmer climate. But those cyclones tend to be more intense. And so now this panel is showing like the tropical cyclone induced precipitation. And so even if we get less cyclone, we get more rain. So the impact of essentially of those cyclones are going to be more important. So even if we get less, it doesn't mean that it's not as bad. Another aspect that the high res is shining compared to the low res is like extreme precipitation. So here we use this like AirX1 day matrix. So it's like the daily mean maximum for every single year. And this is, so you have the observation, high res, low res on the top. And so as you can see, I mean, the high res is just like looking a much better job. Like it's looked like the observation where the low res has a very weak extreme. It's also like reflecting in the global mean. This like improvement when you move to higher resolution is not specific to our model. Like the lower panel show the 9 high res mid mean, and so you can see similar result. Like CSME is one of the models there, but and then like you have the CMF 6 36 mean that is very similar to our low res also. So this is not specific to us so improving resolution really make a big difference when you talk about extreme precipitation. It's not just like the most extreme precipitation. I'm showing the PDF of globally land average precipitation, and you can see that the high res in red is like much closer to the observation in black, especially for precipitation, like for intense precipitation over like 30 millimeters or so per day, and it's significantly better than the low res. So why do we see that? Well, so Ping Cheng, one of the lead of the project, has a paper like that was submitted recently going after that question, and this is just like trying to make a summary of that. So I'm showing the difference like in extreme precipitation between high res and low res at the panel here. And what you can see is that if you look at the resolved precipitation versus parameterized, like most of that difference is actually coming from the resolved precipitation. So that suggests that when you move to quarter of degree, essentially you better resolve like small scale circulation, flow convergence, and you explicitly get more rains. It's not like the parameterized convection that change. It's like really that you start to better resolve like the small mesoscale dynamic that drive like extreme precipitation. This is confirmed, like, so we did like what Ping did like a moisture budget analysis, and this is confirming that hypothesis. So most of the difference is actually coming from horizontal flow convergence. And you can further like split that into like the dynamical tendency and the thermodynamical tendency, and you can see that the dynamical tendency is the main driver essentially of that. So that's something that it was also like not necessarily like expected. Another thing that we did is like we used this amazing tool like the multi-object analysis of atmospheric phenomenon from Andreas Prine. You used to be at NCAR until recently, but he's moved to Europe now. I guess it was a small move from his. Anyway. Here we see like a very different picture again between like high res and low res. So we use like ERA5 as kind of like an observational benchmark, and then we have the high res in the middle, low res on the right. And what you see is that high res and ERA5 essentially show a very similar picture where most of the extreme precipitation, most of the phenomena that are associated with extreme precipitation are mesoscale convective system and CSCs, where like in the low res it's all like jet and front, so very different like dynamic between the two resolution. I mean, now that we show that we have like much better extreme precipitation, and we think for good reason. So we feel more confident that we can look again at projection in the future. And so this is what this slide is showing. So again, like we are looking at late 21st century minus present day. And so you can see that the high res is predicting like much more precipitation in the future compared to the low res. And that this increase in precipitation is mostly like the dynamical contribution is the main driver of that increase, unlike in the low res where it's mostly like extreme precipitation increase due to enhanced atmospheric moisture. So that's the classic picture where it's warmer, the air can store like more humidity, and so you get more rain. The high res is showing like, well, it's actually the change in flow that tend to drive like the increased precipitation, especially in a region of intense precipitation. That was a lot of like atmospheric stuff for the ocean modeling work. So let's go back to the ocean a little bit. So So again, like looking at just like daily extreme sea level, the high res is again like doing a much better job than the low res. So I'm showing you a PDF of extreme daily for all the tide gauge along the Gulf of Mexico. Well, I'm not sure it's all the tide gauge, but like at least 13 of them. And so what you can see is that the tail of that PDF showing like the high res is doing a much better job and very close to the tide gauge, even like closer actually than the altimetry, which had issue when you get close to the coast with resolution and land contamination. So and the low res is doing much less good. This is confirmed, like if you look at the 30-year returning values, like you can see that the high res in yellow is like kind of very similar to the tide gauge and significantly better than both Aviso and especially the low res. So here again, an example where like moving to high res will make a significant difference, and we think that the high res is doing a much better job. So I just want to summarize. So there is a very large volume of data that has been created using HR. We need help to analyze that. We don't have the manpower to do. So we kind of just like scratch the surface, and you're very welcome. The data is available on the RDA. So if anybody's interested, you can just get there or get in touch with me or other people from the Mesa-Clip project. And we really want people to use the data because there is so much to do and we cannot handle everything. So as I mentioned at the beginning, like we are still adding simulation, especially on the high resolution decoupled prediction side. Our preliminary analysis show that there is a lot of like interesting and not actually expecting result from this high res simulation. We show like that high res bring in like many improvements, but it's not the panacea. I mean, we still have like several, outstanding issue in the high res. So I don't think that it's like you just fix everything by moving to high res. Like ENSO is not looking like it's not improved in the high res. Summer precipitation, where I think the convective parameterization is still playing much more important role, is also not looking as good as the kind of like winter extreme that I show you. Like usually the extreme the largest value are in winter. So when you just look at the RX one day, you tend to pick like extreme precipitation in winter, not summer. So I just want to finish saying that in those simulation, we still have convection parameterization. We are not fully resolving TC, but we are still being able to essentially do a much better job with like capturing extreme precipitation. So that was something that, yeah, we didn't necessarily like expected, but there is a lot of value moving to this intermediate resolution in my view. Thank you.
Some time for questions. Rita?
I have a question about the plot that you've shown with SSTs in different members of the high res.
Yeah.
How different are these members? Because I've noticed that in some of them you have the warming hole in the North Atlantic, and in some of them you don't at all. So I was curious, what's the difference in initialization of these different members?
So they are all initial. So we kind of follow like the same protocol than the CSM1 lens ensemble. So we have like the PI control, and then we branched the first ensemble member in 1850, and we run it to 2100. And in 1920, then we spawned the ensemble, the 10-member ensemble, and we just used like random perturbation in the surface temperature. So it's it's a very small, like, keep to the model, and that's sufficient. Create this pattern.
It's really interesting.
So it's just like, I mean, it's just the phasing of the natural variability is different between the ensemble and, but yeah, I mean, the plot were like trend over, I think, like years, 40 years. So depending on the phasing of the natural variability, you can get a very different. Yeah, well,
You showed SST trend from high-res and low-res force simulation, and in
Yeah.
high-res simulation, not just Southern Ocean, every SST is kind of, the trend is really low, if I remember correctly.
the trend tend to be higher, I think,
It's in one of the early slides, I think.
and this one.
Yeah.
So the high res is at the top, so you can see like we tend to have like stronger cooling
Oh,
trend
okay, sorry,
in the high res. But again, like keep in mind, this is like a forced ocean simulation, so we've observed like temperature at the surface, and your SST cannot diverge like much from that. So you bake in the trend, and that's why like the high res and low res they kind of look similar, but still we do get if you look at the difference plot at the bottom, you do get like stronger cooling trend, especially in the Southern Ocean in the high res. Despite the fact that you essentially drive the model with the same trend.
Sorry, I thought that the bottom one is the high-res.
No,
Absolute
that's
stuff.
the difference. I was not very clear, I guess, when I described the slide. Yes.
So you made 2 points. One, you have served vast volumes of data and it's a real challenge.
Mhm.
Second, the high res really matters. If you were to serve the high resolution data at the resolution of the low resolution data, how many of the important differences would disappear? And how
Well, I guess
which would
it's-
still be there?
Yeah, I mean, I guess it depends like what you're looking at. Like for if you look at trend, I mean, you can look like when I show trend using with the CVDP package, for example, we remap everything to 1 degree, so the model the package can ingest that and create all those like plot that I showed you. So for I guess there is no clear answer to that. It's very much depend to what you're after. Like when we did the MOAB tracking, for example, I don't think you can use like force in resolution. We even like we run a segment of the high res, both the historical and future, saving hourly output, so we could do a better job at tracking those like extreme events and all the associated driver of the event. So yeah, we try to save a lot of high frequency. I didn't mention that, but we try to save like a lot of high frequency 6-hourly output, and they are all like available because when you look at extreme, I think you want the temporal frequency and probably the spatial frequency. Now, if you are more leaning toward like climate application and you want to look at trend, yeah, you can probably go degrade the resolution, the spatial resolution, and still get the same answer.
Okay, let's see if there's any questions online while we change the presentation and get any questions online? Roman, please go ahead.
I've to Bob's question, more comment. You serve the ocean resolution at the atmosphere at the atmospheric resolution, right? So there is
No, everything is served on the native grid. So the ocean is at 1/10 of a degree, and the atmosphere is at 1/4.
yeah, right. So the atmosphere can only digest information on a quarter degree, right? So there is you interpolate, right? You're losing resolution in some sense when the atmosphere is forced by the ocean.
Yes, but like the underlying dynamic is still like at 1/10. So yeah.
Yeah, but something provokes the atmosphere to do a better job on a quarter degree.
Yeah.
Okay, let's take Fred one more time. Next speaker is Justin Small. Justin will talk about a comparative study of proportion heat and salinity devices.
And I'd like to add a subtitle that I'm going to talk a little bit about implications of this salinity budget for hydrological cycle estimates. This came in kind of more recently that I got interested and involved in that. And co-authors are listed there and acknowledgements at the bottom as well. And this was primarily funded by NASA Salinity Project. So a brief background on heat and salinity budgets. For the heat budget, the SST feeds back. It affects the bulk fluxes, both the latent and sensible. It also affects the upwelling long wave. So that has effect on the variance and persistence of features. And there's a history of papers that have looked into this, including stochastic models, work done by ourselves at NCAR, and going back to Frankenmuir and Hasselmann. But for the salinity budget, you don't have a feedback of surface salinity, sea surface salinity to the air sea fluxes. Anomalies can or may persist longer, and the damping of salinity featured more due to entrainment and mixing processes. So I want to look at what is the consequence of that for variability of upper ocean salinity and upper ocean heat. But then a couple of slides on this issue of looking at the hydrological cycle using salinity. There was some work done over 10 years ago where people identified, particularly the paper by Durack and Whiffles, two papers. They identified a, see if I can get a pointer to work. Okay.
Here's your point.
All right. Thank you. Okay. Yeah, top panel here is a long-term trend in salinity. And you can see it's getting more salty in the Atlantic and the Pacific. I can't use the cursor very quickly. And there's some relationship to the mean. This is basically evaporation minus precipitation on the bottom panel. And the authors and others are suggesting this indicates a strengthening of the hydrological cycle. Dry areas getting drier, wet areas getting wetter, and consequently affecting the salinity through the freshening from precipitation and evaporation effects. And that was updated by paper in 2020, including some NCAR co-authors. But they kind of confirmed the main finding of that older paper that went into more detail. But then some work done by Nadia Vinogradova, who happens to be the funding manager for NASA, did some very nice papers looking at this using ECHO, which is basically a forced ocean model, but the state that forces it has been carefully, adjusted. So it's called the state estimate. And it's a very sophisticated model. What they found was they tried to estimate the net freshwater flux at the surface using the salinity evolution. And this is an example of a result they got. This is a time series of the global freshwater flux got from the mixed layer salinity. And what you see is, well, it's quite good. Correlations are around 0.66. This is for a looks like 8-year segment, but it's not perfect. And their paper and other papers by the authors identified that oceanic processes were very important: ocean mixing, advection, and entrainment. would basically mess up the relationship, the straightforward relationship between salinity, tendency, and surface flux. So a couple of papers on hydrological cycle. So the approach I'm going to take is to look at salinity budgets in the upper ocean. Again, look at the top 50 meters, which seems to be a useful thickness. Heat content budget. I'll make a comment about salt content or salt, maybe on the next slide. There's a difference between salinity, which is more like a concentration, and salt or salt content, which depends on layer thickness. I'll be using Eulerian methods of grid point regressions, which are fairly standard, and spatial smoothing. And I'm going to follow on from some work done by Frank and others looking at sensitivity to spatial scale, which turns out to be very important in this work. I will focus mainly on non-seasonal monthly variability and use regression technique, which I found useful in previous work. When you're looking at well-closed budgets, you can regress the tendency of the tracer onto the budget terms. And in that framework, values near 1 mean the budget term is dominating. Values over 1 mean that another term will be canceling it. And values near 0 or negative mean they're not important or they're countering respectively. And I'll show one slide on high frequency sub-monthly variability, which does show some differences. And I will gloss over this very quickly, but there are differences between a budget for salt or salt content, and I'll be illustrating this from POP, which will be providing the data I analyze here. If S is the salinity, then the POP budget is not just a tendency of salinity, but there's a dependence on this zeta term, which if you look at the top right here, is in turn dependent on sea surface height. And it's also the advection is written in the flux form, which is the term there. So I've used that, and that's a well-closed budget, but the fact there's a dependence on sea surface height complicates things and makes some things, as you might expect, look a bit like sea surface height variability. And so there's kind of surprisingly large influence of sea surface height. So I also look at a salinity budget where you just have tendency of salinity. I use the advective form for the transport. And to do this, I use daily mean 3D variables, which I had for a segment of the run. So it's not exactly closed. It makes quite a good budget for monthly variability. When you look at daily variability, there's a bit more of a residual due to numerical approximations to this equation using state variables. But I mentioned that goes on. So I'm looking at salinity when I look at a salt-like variable. And I use the high resolution CSM, which is introduced in the previous talk by Fred. So high resolution ocean and atmosphere. And I'm going to point to a paper by Lucas Lorindo and myself and Luan as co-authors, where we looked at the salinity variance in high-res CSM and compared it to other data sets, including Argo, where Lucas has a Argo product where he basically reduces the smoothing that's done in more standard products. So we kind of hope and expect it's more realistic. These plots are showing variance of surface salinity. They're on a log scale, and we compared it with a satellite OISS, top left, and a low resolution equivalent, bottom left. And it may be easier to see from the zonal means that the high res does quite well compared to, say, Argo, as shown in the right panel, where Argo is black line and high res is blue, and then low res is red, and the variance is too weak. Again, it's on a log scale, so it's quite a big difference. And as an aside, the particular salinity satellite product is also a bit weak as well, but I won't focus on that here. So let's go straight into the comparison of heat and salinity budgets. And this will be a number of slides. Will show spatial maps of the regressions between usually tendency and one of the budget terms. And in this case, the budget term is ocean heat flux convergence on the left. So left panel is heat, and the right panel is salinity, where I'm regressing tendency and salinity. This is monthly data, non-seasonal. And what you see is that the ocean heat flux convergence is quite important for the heat budget. The values are positive and mostly between 0.5 and 1. And in the salinity budget on the right, it's even more important, and it's close to 1 in many places of the globe. I'll point out some of these places of the globe actually have lowish variance of salinity. So the question of, is it important everywhere on the globe? But aside from that, you see that the advection is the dominant term there. And these are the budget equations, by the way, for reference. And if you flip that and look at the set of the advection, you look at the surface fluxes. On the left panel is heat, so it's tendency and surface heat flux. And the values in a lot of the globe are quite weak, but there is some high latitude significance. And then on the right is the salinity equivalent, so it's tendency and freshwater flux. And you can see it's quite weak. The whited out areas is kind of poor color bar, but it means it's below 0.2. Okay, so what does this mean for trying to estimate hydrological cycle from salinity tendency? This is kind of pessimistic because if I look in the right panel, there's a very little influence of the surface freshwater flux on salinity tendency. So does that disagree with some of the other papers? And no, it depends on scale. And we're now going to look at the scale. And this is sensitive spatial scale. The same thing as the previous plot, but now I'm smoothing over a 10-degree box. So roughly 1,000-kilometer box. And comparing tendency on the left, this is the heat budget, tendency and advection. And it's a lot weaker than it was on the grid point. Remember, in the grid point, this is mostly red, near 1 in some areas. And this actually, in some of these areas, is actually an Ekman advection is probably the important thing. Done work on that previously. For salinity, which is on the right, advection is still important, but it's less so than it was on the grid point. So instead of nearly 1 everywhere, it's nearly 1 in quite a lot of regions, but it's also small in other areas. So what that means, I'm not sure if I show it in the next slide. I do. It means that in some regions, you can use surface flux to estimate tendency. And for the heat, which is on the left, you can see it's a lot of regions. So again, this is the spatially smooth result between tendency and surface heating. I've added the mixing here, but it's mainly the surface heating. And you see these very large values. For salinity, not so strong, but there are regions of the globe where it's near 1. So you can use surface flux to estimate salinity tendency, maybe learn something about the hydrological cycle. This is monthly, non-seasonal. And just a slide that you can decompose things like the advection into Ekman and geostrophic, which is a very standard thing. Here on the grid point, it's more dominated by geostrophic flows than Ekman. But if you spatially smooth, you find Ekman's playing a bigger role, both for heat and salinity. Okay. And then a slide on high frequency variability. Initially, I was surprised. I thought for high frequency variability, things like transient precipitation events and so on would have a big impact. So I was expecting to see a bigger impact on the grid scale. And there is, but it's not overly dramatic. This is for heat, relationship between tendency and surface flux for variability of less than 2 weeks. And in some areas, yes, it's near 1, so surface flux dominating, but other areas it's near 0. And this is the salinity equivalent on the right. It's kind of a similar story. But once you do the spatial smoothing, you actually very quickly get a different result where the surface fluxes dominate kind of totally, almost totally. For heat, it's very strong. And for salinity, it's also very strong, except near the equator. So in the tropical region, the ocean dynamics still important. And one thing here is you don't have to actually smooth it much to get this result. These are for 10 degrees smoothing, but I looked at 3 degrees smoothing and you get a similar pattern. So really it's saying, well, on the grid scale, you get this kind of result on the top. But it's just those really fine scales. By 300 kilometers smoothing, you're getting something more like the bottom. This actually goes back to Bob's question. And I've seen this before for some, actually I may get confused if I address Bob's question now. I'll talk to you later about that. This is a case where there's a strong sensitivity to scale. In other cases, I have not found such a sensitivity. So I'll try and move on. I wanted to reconcile some of the high-res results with previous work. And so if you remember one of my earlier slides showing on the grid point, advection was totally dominating salinity. So that what does that say for estimating the hydrological cycle from salinity tendency? Well, the top panel here, this is a figure from paper by Vinogradova and Pond, 2013. And it's a correlation between salinity tendency and surface forcing from ECHO for sub-12-month timescales. And you see in these regions of the globe, there can be quite high values, but there's also regions such as the tropics where it's near 0. And the bottom panel is from the high resolution CSM, but this is the spatially smooth case. So this is actually the same plot I showed earlier, but I've shown a different center longitude, I think, to try and do my best to match top plot. I'm sorry I didn't do exactly the same plot. But if you look carefully, they're actually quite similar. You get these areas such as South Pacific, where you have very high values, the kind of subtropical Atlantic, you get this band here, Pacific as well. And some of the minima also relate between ECHO and high-res CSM. So the results are consistent, but you have to do a spatial smoothing to CSM to get something that looks like ECHO. ECHO is a 1 degree ocean for reference. So ECHO is actually doing quite a good job compared to the high-res, if you kind of believe in the high-resolution CSM, as long as you apply this smoothing to the high-resolution CSM. So I'll summarize. The salinity budget, non-seasonal, it's definitely dominated by advection on the grid scale, and that was even more than the heat budget. I should have removed that second item. I didn't show the seasonal cycle this time. On larger spatial scales, though, surface flux plays an important role both for the heat budget and for the salinity budget. And the thing kind of interesting result, the large scale salinity tendency can be used to estimate selected regional hydrological cycle, as suggested, going back to Durack et al., but also in the paper by Nadia. But there's questions about what time scale, and I showed monthly and high frequency here, but the Durack paper was on long-term trends. I have not looked at that yet. And there's a kind of interesting question, how do these results relate to the long-term trend? And finally, some important regions are not well estimated, including the deep tropics, where ocean dynamics is very important. And the next steps, some things we're thinking of, Lucas has been looking at stochastic models for ASC interaction, and with Luan and myself is interested in doing this for the mixed layer salinity. Want to compare more with ECHO. As I said, there seems to be some consistency. I'm working with Ivana Cherevecki on that. And also a timescale dependence, getting more interesting now, not just the high frequency, but also the long term, which I didn't really address. And Dan Witt, and also I know Luan and Lucas will also be interested in that, try and relate it to the earlier paper on trend. So I think I'll finish there. Thank you very much.
Questions for Justin? Dan?
I'm interested in this and the results you have about the spatial smoothing, increasing the correspondence between the models. And do you think that that is getting at spatial coherence of the tendencies themselves? And also maybe related, like, do you think that there is any dependence on the grid scale of the model and how sensitive it is to the higher frequency tendencies?
So on the second bit, on the grid scale, as I say, that we identified some consistency between ECHO and high-res CSM, and they got very different grid scales. But they are consistent when you look at the large scale. Then the first part, really when I was looking at snapshots from the daily analysis that went into the high frequency, and you can see synoptic storms are going by, synoptic atmospheric events, and they're having some influence, and they tend to be large. So evaporation signals tend to be fairly large. Precipitation signals vary from being fine fronts in the atmosphere to broad precipitation. But then the ocean advection, you can see it as a lot of it is the fine scale. It tends to be very large amplitude. So that's why it's dominating the grid scale. But once you do the spatial smoothing, you're identifying coherent large-scale patterns. A lot of them are from the atmosphere, driving evaporation and precipitation. So yeah, they are coherent patterns, I would say.
Well, it's really kind of the same question. Lucas's prior work, he identified the atmospheric Rossby radius as the scale at which you see this transition. Has he applied the same analysis to the salinity variance equation to see if does the fact that there's, a negative feedback in the heat budget, does that somehow influence the scale of transition?
Yeah, we haven't. So the answer is we have not looked at it, and it's an interesting one to follow up with Lucas. Lucas actually has more sophisticated ways of looking at spatial scale, as you're kind of inferring, than my box averages. It has some sophisticated spectral wave number frequencies space analysis, which I think could add a lot to this as well.
Any questions online? Well, if not, let's think Justin one more time. 30-minute break until the seminar at 11.
Impact of this parameterization on energetics and circulation of global ocean model. Here I try to describe mesoscale eddies, how they are represented in ocean models. So first of all, these are eddies with relatively small size, between 10 and 100 kilometers in mid-latitudes. And they are responsible for horizontal mixing of properties like momentum, salt, and temperature. And eddy permitting ocean models quarter of degree, they are missing major part of eddy kinetic energy associated with this mesoscale eddies. And because we are missing this eddy variability, we also missing the mixing which is associated to mesoscale eddies. And so in 2014, Jensen and Held proposed an approach how to deal with mesoscale eddies in eddy permitting ocean models. We can acknowledge that grid resolution is sufficiently high, and so we can just energize eddies on a given grid. And that way we will increase the resolved mixing, and resolved mixing will help us to fix other issues. For example, we can release APE with enhanced resolved mixing, as it was shown in work of Elizabeth Inkowski. So our approach of parameterization is shown here. So we are following spatial filtering approach similar to large eddy simulation in 3D turbulence. So we introduce a Gaussian filter, and then we extract the unresolved or subfilter advective fluxes which correspond to scales smaller than the filter width. And also for quasi two-dimensional fluids, we can assume that this advective flux can be represented as a divergence of two-dimensional momentum flux tensor. It's shown here. So we diagnose eddy fluxes T large from high resolution climate model CM2.6. It has resolution 1/10 degree and can resolve mesoscale eddies in mid latitudes. And to propose parameterization, we try to predict these momentum fluxes having some inputs. So we are using inputs which are popular in other subgrid parameterizations. These are gradients of velocity field. To extend capability of our parameterization to learn from data, we learn not a point-wise parameterization, but we increase a spatial stencil to 3x3 points. So here you can see a schematic of parameterization. We take 3 components of velocity gradient tensor. These are 2 components of strain rate tensor and vorticity. Then we consider a spatial stencil of 3x3 point. We flatten these input features into one vector. It has dimension of 27. We pass it through a neural network, and we predict 3 components of momentum flux. So here I show example on near Florida Strait, but we apply it globally for the full ocean. And so one important point is to include physical constraints in our parameterization. It generally helps to improve generalization, but also we can believe to what we do a little bit more if we satisfy physical laws. So first of all, there is rotation and reflection invariance. In ocean models, sometimes like in MOM6, it's preserved up to numerical precision. Here, just for simplicity, we achieve this invariance by data augmentation. It means that every training sample is rotated or reflected. And that way we have equal contribution from every rotated image. And also we have few hard physical constraints, which include conservation of momentum and angular momentum. It's achieved simply by deciding what our output features. So our output features are momentum fluxes. Consequently, we conserve momentum, and also the momentum flux tensor is symmetric. Consequently, we conserve angular momentum. Also, the parameterization is Galilean invariant. It is achieved by choosing the input features. The input features are gradients of velocity, and so they are not sensitive to Galilean transformation. And the final property I want to point out is unit invariance. It's often missing in data-driven parameterizations, but it was shown to be important for subgrid closures, for example, in the work of Prakash in the context of 3-dimensional turbulence. So clearly, if we learn a mapping between velocity gradients and momentum fluxes, there is one missing length scale which doesn't allow us to create this mapping. And so we restore proper dimensional scaling by introducing another one, length scale, which is a grid spacing. And so having grid spacing and velocity gradients, we can restore unit invariance as follows. So we normalize velocity gradients by their second norm. So now the input feature to a neural network, which is shown by large T here, the input features are not sensitive to rescaling of units anymore. So we always have the same prediction. And then we restore dimensionality of outputs by multiplying prediction with length scale and with time scale. Time scale, it's gradient of velocities. Okay, and we compare it to our baseline approach where we do not impose any unit invariance scaling. And so what I'm showing here, we want to show that unit invariance is important for generalization. Generalization in machine learning means the following. We train our parameterization in some particular scenario, and then we want to know how it works on completely different data not seen during training. And so here I pick the fields corresponding to the surface of the ocean at a grid spacing of 0.9 degrees. It's a grid spacing of a coarse ocean model. And so we have true diagnosed subfilter fluxes, and we have predictions by model with dimensional scaling and without dimensional scaling. Even on data which is similar to training data, we have slight improvement in performance quantified by higher R-squared and higher correlation. But what is more important, we can show that when we change the resolution of the coarse grid, we still can give a very reasonable prediction with similar R-squared and correlation, but the baseline approach cannot do it. So what happens here, because we do not have proper scaling, we give a prediction which has relatively high correlation, 0.7 here, but the scaling in front of the prediction is wrong, so R-squared is negative because of this. And so here I demonstrate that this effect holds for a range of grid resolutions and range of depths. So here the green square corresponds to the upper panel and orange square corresponds to lower panel. And all other combinations of grid spacing and depth show that we can have a reasonable prediction just by training at one depth and one grid spacing. But our baseline parameterization often has negative R-squared just because of missing scaling. A final parameterization is trained on all of this data. Because we have it, why not to train? Just we want to be sure that if we will use it in a scenario which is different from training, it still will give reasonable prediction. And we evaluate this mesoscale parameterization in MOM6 ocean model in two configurations. I will show a few slides with NeverWorld 2 configuration. It's a wind-driven adiabatic model with 15 layers. And most of the attention will be devoted to global ocean simulation OM4 at 80 per meter resolution. It was run for 60 years with historical forcing. So some details of implementation. In an ideal world, we could just learn subgrid fluxes and learn dissipative operator, but it didn't happen. So we must supplement our parameterization with big harmonics Makarinsky model. It's already used in both of these configurations. Also, we found that in idealized double gyre in global ocean model, neural network can work as is without any tuning. However, in NeverWorld 2, we had to perform some tuning for numerical stability. Unfortunately, it often happens with this configuration with other backscatter parameterizations. Okay, now let's consider what can happen if we increase resolution. So we want to increase effective resolution. And here we consider the optimal effect which we can achieve by increasing resolution. So we plot the difference between high resolution ocean model, coarsened, minus coarse resolution ocean model. And we consider two metrics related to energetics and one metric related to ocean circulation. And so when we increase resolution of ocean model, we see that we increase eddy kinetic energy. Eddy kinetic energy is increased near the western boundary currents and in ACC region. ACC region is here for this idealized simulation. And because we increase eddy kinetic energy, also there is more mixing associated with mesoscale eddies, and so the mesoscale eddies, they release available potential energy. It mostly happens in ACC region here, but also you can see that potential energy is released from ocean gyres as well in rest of the domain. And finally, I want to point out that if we remove potential energy from Southern Ocean, we also should reduce the transport through Drake Passage. We should reduce barotropic stream function in this region. So here by contours, I show barotropic stream function in coarse ocean model, and in color, I show the difference, what happens when we increase resolution. So as you can see, the transport in Southern Ocean was reduced. And so we also observed that commonly the change of APE and change of transport, they correlate to each other, especially in a part of the simulation which is similar to channel, like Southern Ocean. In the rest of the domain, there is no such clear correlation. So now what happens if we plug in parameterization? You can see it here. So first of all, as expected, we increase eddy kinetic energy near the western boundaries and ACC region. And these more energized eddies, they can extract more potential energy from the mean flow. So we again can see reduction of APE in ACC region and in gyres. And finally, again, we see that there is a similar change of the circulation in the Southern Ocean. So we again reduce transport in ACC current. So based on this, we conclude that effect of parameterization is qualitatively similar to increasing effective resolution of our ocean model. And now we want to figure out if this effect is similar when we consider it in a global ocean simulation. And so while there are some qualitative differences, quantitative differences, I want to prove the point that the effect is similar. So first of all, we increase eddy activity near the western boundaries, like in Gulf Stream region and Kurashio region, in other Agulhas, Malvinas currents. And also we increase eddy kinetic energy near the ACC current. Somewhere you can see blue spots, so it's reduced eddy activity. Probably it's related to small averaging time interval, which is 1 year here. And then we see that same as in idealized configuration, we extract potential energy. Mostly we extract potential energy from the Southern Ocean. Another noticeable place is subpolar gyre in Atlantic and subpolar gyre in Pacific Ocean. And finally, we again can see the correlation between the places where we extract potential energy and places where we reduce the transport. So again, you can see that barotropic stream function was diminished in Southern Ocean. Okay, so now we want to consider another one effect, the effect on the stratification. So it's one of most important properties in the ocean. And in particular, stratification is used for tuning and calibration ocean models. For example, our unparameterized ocean model almost do not have drift in temperature. So here I show spatially averaged potential temperature as a function of depth and time. So as you can see, away from the upper layer, there is almost no drift. And it was achieved by some tuning of parameterizations and numerics. And when we include our mesoscale parameterization, we see that there is a cooling of temperature everywhere in the ocean. Not good wording. You can see it. There is cooling. And so I believe that this cooling is very reasonable and this is the right thing to do. Because if we release potential energy, we redistribute heat polyward, but also the heat should go upward because it's adiabatic redistribution. Second, I've seen cool drift in various scenarios. For example, increasing horizontal resolution of ocean models, including Gent-McWilliams parameterization, or including isopycnal diffusion. So our approach, it's related to all of these three processes because we enhance mixing, so we are similar to mixing parameterization, and we increase effective resolution of the ocean model. And here I show some metrics of the polyward transport. Because as I said, there is a release of potential energy from Southern Ocean. Probably it should be related to some additional northward heat transport. So as you can see here, we increase heat transport by 0.5 petawatts. I think it's a little bit too much, but probably it's a reasonable outcome of reducing potential energy. Sometimes I've seen a really big spread in core simulation in polyward heat transport. But if somebody has comments on if it's expected or not, it would be appreciated. Also, because we move more heat polyward, so there is a reduction of the ice thickness in the Antarctic. Similar effect of backscatter was reported, for example, in Juricki paper. And finally, I show the AMOC in contour lines and this response in AMOC in color. So we reduce strength of AMOC. I think I'm not ready to fully explain why we should reduce strength of AMOC. Here I also happy to have some input. And so here are our conclusions. We propose a single data-driven parameterization of mesoscale eddies, which was trained and can work for a range of resolutions and depths. And we show that the important way to achieve this generalization is imposing unit invariance property. Then the impact of this parameterization is similar to increasing resolution, which include increasing eddy kinetic energy, release potential energy, weakening of ACC current, and cool temperature drift. There are less obvious effects. They are summarized here. And finally, I want to point out that OM4 configuration, our control run, clearly was tuned to preserve the temperature, similar to World Ocean Atlas from the very beginning. It doesn't even require spin up to preserve it. And whenever we try to parameterize mesoscale eddies, there will be drift. And that's why we cannot see a positive systematic effect of mesoscale parameterization because we drift away from data to which it was tuned to. So maybe this is some future direction what to do with tuning. Maybe such parameterizations can be used as a tuning knob because right now mesoscale parameterization, they are not used in any permitting models. And so this one can be used without killing eddies. Thank you. I'm happy to answer questions.
So Pavel, you ran it for one core 2 cycle, is that right?
One core cycle.
Yeah, and so you didn't continue to run and see if the drift reduces after it spins up more and what the ultimate bias is, because normally it takes 4 or 5 core cycles before like something slows down. Do you expect that it might? I mean, did you see? It looked like it was continuing to increase as you went, but like that was in the bias, not in the rate,
I
right?
see. You mean this one?
Yeah.
Yeah, it might happen. So I want to say that my experiment is a little bit different from what people commonly do because I start with spun up simulation. I start after 4 cycles of unparameterized model. So it would be much more clean to perform, of course.
5 cycles with the parameters, yeah. Okay.
Thanks, Pavel. Can you go to your last slide? I was confused. Your summary, you start saying that it can be used for a range of resolutions. But then one of your last bullet, the one before the last bullet point, you say intermediate, the last one. I was thinking, because in OM4, you have no parameterization to begin with, and then you added your parameterization. What if we would add, try this in a ordinal workhorse, or 1 degree, or our 2/3 degree? What would be your suggestion? Should we have with the ready, without ready, replace GM on top of GM?
Well, I think at 1 degree resolution, buoyancy fluxes also should matter. And so we have Drupal, WAD, and ELSI. In our project, they try to incorporate data-driven parameterizations for buoyancy fluxes as well. So this might be one possible direction.
But then we should not try yours on tutors.
I think it may be just not enough. Because the importance of momentum fluxes, I think it starts from 1/2 degree and up until any resolution. But buoyancy flux is more important than 1 degree. I mean, my parameterization can generalize offline, of course, resolution, but I cannot promise that there will be some positive effect online.
Just to clarify that last point there, I mean, I usually think of a tuning knob as a poorly constrained free parameter. But as I understand, your parameterization doesn't really have free parameters. You've constrained it from the training data. In what sense do you consider it a knob?
That's a good question. There is some freedom because whenever we parameterize the filter fluxes, there is always a decision what is referred to the filter scales, what is the result scales, and it's controlled by filter to gate ratio parameter. So here I think it will be 3, but it can be 1 or 4. There is full range of these parameters, and this is it will be responsible for the strength of this parameterization. It's very
Without really understanding this very well, is that done at the training stage or in the model run stage?
well. Right now, it's done at the training stage, but mostly to make this study clean. We can also do it after, but by multiplying it by some.
I'm gonna ask a question. Prerogative sharing here. So we've seen a lot of similar results with the Miki backscatter qualitatively, the drift, the sea ice, the heat transport, AMOC, a lot of this stuff is increasing kinetic energy. I mean, there's a lot of similarities compared to like Miki backscatter. Have you compared to results using other backscatter, or I don't want to call this a backscatter method, there's more to it than that, but have you compared to backscatter methods to see if there's differences?
Well, I was performing such comparison for 5 years runs. So for short simulations, we can see similar responses in North Atlantic, which I did. Maybe there is some similarity in ACC, but I didn't pass it through the full analysis on 60 years. I think there should be some similarity. I'm comparing it to a paper from GFDL on the remote versus local scatter. I think the main difference is how it affects the net flow. The backscatter by Jensen Hell makes everything stronger, eddies and wind flow. This one is not necessarily works like this. It definitely makes stronger eddies, but wind flow sometimes is not. Okay. Whether or not it's good or not, I don't know. Slightly different.
We have a question.
Oh, yeah, thank you. Wenda. Quick question.
Hi, let's talk Pavel. So I have a question about the weakening AMOC. So I'm wondering if you check the stratification in those high altitude North Atlantic. I remember you showed that the available potential energy decreases in the polar gyre, but what about those deep water formation regions? Did you see like a significant restratification there, which reduces the AMOC?
Thank you. It's a good question. I didn't check yet stratification. I will do.
Yeah, Akash has just replied. He's on plane, so he's not, he had requested yesterday or tomorrow, but the schedule didn't work.
Sorry.
Yeah.
Well, are there any other questions for? We have a little bit of extra time. I will do that to you.
So Pavel, how about the bigger concept of unit invariance? Like here, you're from the deformation radius up, like you're always in sort of the same dynamical regime. But if you had physical length scales that were coming in as well as the grid scale, how would you contemplate, like, so if you were trying to make this as a, you know, a strongly eddy rich parameterization and wanted to go all the way down to like 1 kilometer runs, how would you handle the unit invariance in that case?
Well, so here we use grid spacing as a length scale. We can use additional length scales, for example, Rossby deformation radius. The issue is the following. I wasn't able to show that including additional length scales actually help to improve upline performance. So probably it's some issue with data-driven parameterizations. No matter what the eddies and what the filter scale compared to the eddy size, we always can implicitly infer the strength of mixing from the result field itself, especially if we are working on some spatial stencil. So if I will use input features in one grid point, there is a slight improvement of additional length scales. There's a small information we pass to neural network, it's able to detect that.
Is our third speaker online, Xiaorong Wu? Yep. And I know, are they ready? Because we're half an hour early on their talk. I don't expect them to be ready right away.
What's the biggest?
Yeah, I'm ready. I can go anytime.
Okay, or were you gonna suggest something?
The one talk after the break also is a withdraw.
Yeah.
We can try to shift the very last,
That's a good idea.
the survey to some time, and that way we can go to the public.
Yep. Okay, so Xiaorong, I think we'll have you next, and then we'll have short discussion, question, Q&A, and then a break. Maybe after the break, we'll do the thing we were gonna do last, we'll just put it after the break. Thank you, Pavel. All right, and it's go ahead and share your screen. I know you're working with the guys in the booth on that.
I'm having some issue with the permission, so maybe it will take a minute.
I think we have extra time.
We have time. All right, we can see your slides, and you're in presentation mode. Are you ready for me to introduce you?
She left the meeting.
Oh, I see.
You gotta log out.
Reg, you gotta
Restart. Anybody know any good jokes? Anybody know any good jokes?
Mics pick up everything.
Oh, I know. They have to be internet appropriate. You guys want to watch a strange AI generated video? You see that tomorrow.
Okay,
So, is it good now?
yes, let me introduce you, and then you can go. So our next speaker and last speaker for this session is Xiaorong Wu from NYU, working with all the people there, several of whom are local. So go ahead, Xiaorong.
Yeah, hi everyone. I'm Jarong. I'm a postdoc at NYU. I work with Laura Zana and also David Jonganier here at NCAR as part of a project at LEAP, Learning the Earth was at Artificial Intelligence and Physics. It's a NSF/STC at Columbia. And the full list of co-authors here. It's my first time at a CSM workshop, so glad to be here, although virtually, to talk about our recent work on learning air-sea flux algorithm directly from observational data. Okay, so our goal here is to learn these turbulent fluxes. There's 3 fluxes: the momentum flux, both along wind and crosswind, sensible heat flux, and latent heat flux. So these are result from kind of a downward turbulent transport in the atmospheric boundary layer. And we've defined them so that the positive sign is from the air to the water. And our goal is to represent them using state variables. These are variables in the surface layer, so wind speed, atmospheric temperature, humidity, sea surface temperature, current speed, etc. Because we need this algorithm because these variables in green are either already existing prognostic variables in GCMs, so we use them to compute fluxes as we run the simulation, or because these green variables are more easily observed, so we take measurement either in situ or satellite of these green variables, and then we use the flux algorithm to compute the fluxes, and that maybe we make up flux products that we can use to force either the atmosphere or ocean only model. So the current algorithm we have are these bulk algorithms. So these are these turbulent fluxes expressed as a coefficient times the magnitude of the relative wind speed times some difference of quantities between the atmosphere and the ocean. So these algorithms are physics-based. There is an underlying Monod-Nabokov similarity theory of the boundary layer, but there is a empirical aspect to it, meaning that some of the parameters are fitted to observational data. So here's an illustration. You take the input variables, pass it through the algorithm, and get the fluxes. These algorithms are also iterative, so depending on the number of iterations, the computational cost can differ. There are different versions of these algorithms. So CORE, NCAR, and ECMWF are some common choices. And there are also ad hoc corrections sometimes applied, for example, the cool skin, warm layer correction or some gustiness correction. So to summarize, it's an algorithm based on physics, but it has a strong flavor of empirical kind of parameter fitting and corrections to it. So the issue is that because there are different existing different algorithms, using different algorithm can have a considerable impact on your flux estimation. So here is a plot showing in the zonally average turbulent heat flux, so latent plus sensible, in a flux product. And the 2 black lines, one with crosses, one without, are computed using 2 different bulk algorithms. And you can see that the profile are pretty different. And considerably, this will have an impact on our general circulation model. So there have been sensitivity studies looking at the effects of using different algorithms on these things of interest. And the other issue, apart from that, is the bulk algorithms are designed to represent basically the mean value of fluxes given the input So here is an example. The each individual dots are measurements, and the lines are bulk algorithms. So the lines goes through the dots, so it's predicting one wind stress at each wind speed. But there is some variability in the actually measured fluxes that are not captured by bulk algorithms. So, and these variabilities might be something we want to retain with our flux algorithm, depending on your applications. And to do so, the one way to do so is to introduce additional inputs, for example, sea state. But that also means you need to now solve for some additional prognostic variables, and in this case, couple a whole wave model to your GCMs. Or you can try to do some stochastic parametrization, being kind of agnostic to the exact source of this perturbation. And to do that, we also want to have some idea of the degree of this spread. And that is the motivation of this work. We want to learn a flux algorithm directly from data. And we want to kind of have a quantification of the spread around that mean prediction. And we use data from NOAA's physical sciences laboratory. So there are about 10,000 samples from these shipborne direct eddy covariance measurement, and they're hourly averaged. Unfortunately, we don't have high fidelity numerical simulations to give us anything closer to these direct measurements. So these eddy covariance measurement remains our valuable data set to constrain basically any flux algorithm we put forward. And as I said, we directly predict the fluxes, and the algorithm itself is a probabilistic one, meaning we are assuming a parametric distribution condition on the inputs. So we're not just predicting one value given one set of inputs, but some of a distribution. And these references go over kind of the methodology and also its application recently in geosciences. Yeah, as I said, we are assuming a conditional Gaussian distribution. So for each flux, we have two parameters to fit, the mean and the standard deviation. And we use so two artificial neural networks, ANNs, to fit them, and the theta and the phi are the parameters within the neurons, so basically the weights and the biases. What we're doing is to minimize the negative log likelihood, so basically maximizing the likelihood of observing all these samples. Through these optimization procedure, we adjust our theta and phi. So once the neural net is trained for a given input X, we predict a mean and a standard deviation. So this is just a animation showing how the neural networks is able to learn both the mean and the standard deviation simultaneously over epochs, given some data. And we did this through trials and errors. Eventually, we used 5 inputs. Here are wind speed, temperature of the atmosphere and ocean, relative humidity, and surface pressure. And we're definitely operating in a data pool regime. So there's we had to be careful to do careful cross-validation and some techniques to stop the overfitting, but I won't go into details in this talk. And so here I'm showing some evaluations of this new RC flux algorithm. Here are the kind of evaluation for the mean part, how good that correlates with the observations. So on the x-axis is the measurement, and on the y is the predictions, and the orange is the ANN, and the black is our baseline core 3.0. Basically, they look pretty similar, but the ANN is having slightly higher R squared, so slightly better statistical correlation with data across all three fluxes. And another interesting thing we found was that when we evaluate these statistical scores, they vary quite significantly across regions. So our data set is composed of cruises that sample different regions of the globe. And the disproportional amount of the data is actually in the tropics, 58%. And the thing with different regions, basically the distribution of the inputs are different. So the distribution of wind speed, temperature difference, and relative humidity are will change depending on the region. So when we are evaluating the statistical correlation R squared over different regions, sometimes the score changes dramatically. For example, for the sensible heat, it drops to almost 0. And intriguingly, in the tropics where it's most sampled. Yeah, so that's something worth pointing out, I thought. But overall, for across geographical locations, the ANN is also just marginally better than the bulk baseline. But we thought it shows some kind of generalizable properties of the ANN as well. Here is a different way of evaluating the predictions. So here I'm showing the prediction of both the mean and the standard deviation, and it's on a grid of uniformly gridded wind speed UA and temperature difference TA minus TO. So the leftmost is the prediction of the sensible heat itself, and the middle plot is the prediction of the standard deviation around that mean prediction. We think it gives us a reasonable prediction of the spread, so the red. You see that it's higher in the higher wind speed, and also kind of higher for larger temperature difference. And another thing to point out is that we are limited by data. Basically, the third plot shows kind of a data density. This is all the training data. And we have very few high wind speed samples. But at least the ANN extrapolates pretty smoothly outside this training, outside the region where we do have training data. This is another way of looking at the prediction. Now I'm comparing the mean, the sensible heat prediction between ANN and the core 3.0. There is some interesting difference, although the structure looks pretty similar, and most noticeably, because the ANN doesn't assume that functional form, it's not strictly down gradient, so you will see some small but finite fluxes when the temperature difference between atmosphere and ocean diminishes. Right now, it's not clear if that's a desirable feature, but I just wanted to point that out. We're not assuming, we're not posing any constraints that it's down gradient. Okay, so now we have a kind of bulk-like algorithm learned directly from data. We wanted to test it, and the test bed we chose for the first test is this really simple single column model of upper ocean, because we assume And the upper ocean will be the most tightly coupled to surface fluxes, and also we're interested in seeing how the flux algorithm interplays with the boundary layer parametrization. So we implemented this in Gotham and General Ocean turbulence model. It's solving this 1D equation where the time evolution of velocity, temperature, and salinity is given by mostly a vertical transport term. And these terms are parametrized either by a KPP scheme or a K epsilon scheme. So the surface flux here is a boundary condition for the set of equation, but it can also affect the vertical mixing scheme. For example, through the buoyancy flux, it will change the KPP, and it will also serve as a source of kinetic energy for the K epsilon scheme. And we're running the model in a forced way, meaning, but this is the standard way of running these cases in Gotham. Basically, we compute the fluxes offline based on the measured input variables. We are here only modifying the turbulent heat fluxes, so sensible plus latent, because these are assumed to be more uncertain than the momentum fluxes. So we are keeping momentum fluxes and long wave, short wave radiation the same. Yeah, so we did this. We used the observations at Ocean Weather Station Papa. We compute the fluxes using either ANN or our baseline model Core 3.0. And then we use these fluxes to force the single column model. Before looking at the upper ocean state, here are how the fluxes look themselves. Interestingly, there's kind of a seasonal dependence already when you look at just the fluxes. In the summer, and if there is pretty small heat fluxes, and then the ANN and Core 3.0 are pretty close to each other. And in the fall, there are larger flux values. And when you see these really large values, say around October 20, then the algorithms start to differ more. But overall, also plotted in dashed line is another bulk algorithm, NCAR. But overall, the difference between ANN and any bulk algorithm seems to be larger than the difference between two bulk algorithms, so Core and NCAR. Also, the shaded orange is the predicted standard deviation. So interestingly, most of the time, the core flux is within this plus minus sigma. We did that with these deterministic cases with just forcing with the mean. And then we also did a set of stochastically perturbed fluxes using these predicted envelope of standard deviation with noise generated by an autoregressive processes. So each individual thin orange lines are one ensemble member of a flux time series. And so we run 20 of these, and we did kind of 4 years. So here is a typical annual cycle of like how the surface, how the ocean temperature looks like at this station. So you have the deep mixed layer, and sometime during the spring there's restratification, and then over the summer there's some heating at the surface, but then in the fall the mixed layer deepens again. But there's kind of a limitation with using a single column model, ignoring horizontal advection. There is an annual heat flux imbalance at this site. So if we keep the simulation running it will gradually drift away. So we did a monthly restart. So we restarted each of these black dotted line to kind of track still the observed mixed layer depth. So we're focusing on the effects within each monthly window. And for the same reason, we are not trying to compare directly with the observations of mixed layer depths and SST, but focus on the response. So how it looks, how different it looks in the ANN forced case and in the core forced case. So here is a heat map showing the response in SST. So for each month, and there is one row for the K epsilon model and one row for the KPP model. KPP parametrization. So basically the response looked pretty consistent whether you use this flux in combination with K epsilon or KPP. And in terms of the response, we're seeing on the order of magnitude of like 0.2 degrees in SST and maybe 2 meters in mixed layer depths. And these also have a very strong seasonal pattern. And for the month, so this third row is the monthly average heat flux difference between ANN and bulk. I'm adding it here to say that these response that we see is not a simple and heat budget, because the months where you are putting less heat in does not necessarily correspond with the months where you're seeing the response. So there is some interplay with the vertical mixing scheme. Oh yeah, and I forgot to mention that the hatching of the months are where we don't see consistent trends between the 4 years that we ran the model. So the parts without hatching is where the pattern is strong. Also, to put this in context, these are the magnitude that we get from changing the flux algorithm, where on the bottom is the response we get from changing the mixing scheme. So if we change the K epsilon scheme to KPP, we will see a stronger response in the SST and on the other 0.7 degree and maybe 20 meters in the mixed layer depth. So the magnitude in changing flux is definitely smaller than changing mixing, but when you change the mixing scheme, you mostly see a uniform response over the year. So you either always and the decrease mixing, so you always have a shallower mixed layer, and the trend is uniform over the year. Whereas when you change flux, there is a seasonal pattern. So I hope this suggests that if we want to fix some bias that is seasonal, there is some hope that we can do it with changing a flux algorithm. And finally, this is the spread in our ensemble runs. These lines are showing, so blue is the deterministic run. The magenta solid line is the mean of the ensemble, and the shading is the standard deviation of the ensemble. So we are seeing mostly the ensemble mean tracking the deterministic. So there is not a systematic drift from introducing the perturbation, but so I'm not plotting the drift here, but there is a spread. And most noticeably, it's during the restratification period. When you introduce noise, it can affect the timing of this event this is a pretty dramatic event, and when the timing changes, basically is where you see the spread in mixed layer depth across April and May. So is the summary. We proposed a probabilistic model for air-sea flux, and I'd say it's a bulk-like algorithm. It takes similar inputs as bulk algorithms, even just a subset of it. So if we want to implement it, it shouldn't be that much work to kind of swap out the bulk algorithm and try this new ANN in the coupler that is already existing. And in terms of the mean prediction, we have slightly better statistical correlation, seems like 2 observations. And the variance, so the standard deviation part, provide us a quantification of this spread around the mean, and it could be used for stochastic parametrization. And our preliminary implementation in a single column forced upper ocean model shows there's strong seasonality in both the predicted flux differences and the response. But because of the limitation of the single column model, we would really want to try this either in a kind of forest ocean model, either globally or regionally, or a coupled CESM run. And although the response we're showing are kind of small in magnitude in the single column model, there is a large spread when we look at the ensembles. So this can have implications when we do couple this to nonlinear processes like horizontal advection. Yeah, so that is my talk. Here is the manuscript in preparation, and I'm happy to take any suggestions or questions. Thanks.
Questions in the room or online? Frank first.
Very interesting. One advantage of the similarity theory-based schemes is that it can accommodate within their iterative algorithm input data at different heights. So, if you have a buoy that has a thermistor at 2 meters and an anemometer at 5 meters, you can handle that. Similarly, in models, the model lowest level might be at different heights. Does your ANN accommodate inputs defined at different elevations, or is it all trained assuming the data is at a particular height?
Yeah, so we ended up on these 5 inputs, which, as you pointed out, doesn't include heights. This is mostly due to it's from trial and error. Basically, initially I wanted to include heights, but these measurements, they are kind of measured around similar heights. So it ranges kind of from 17 meters to 19 meters. So it's not a big difference. So it makes the network hard to learn, basically the dependence on heights. So yeah, definitely if there should be room to further refine this. So yeah, eventually I think we would want to have some height dependence. It's just a matter of if we can learn this from this training data set, or if we need additional methods to get that. One thing is we could generate kind of synthetic data from bulk algorithm at different height and pass the network through that first, and then further refine on these measurements at the same height, basically.
Thank you.
Yeah, thanks.
Baylor?
Sure. Very interesting talk. When you do the autoregressive model, what does the decorrelation time end up being? So are you really drawing from a new distribution every time, or repeatedly with persistent biases? Because that would really matter when you put it into the mixed layer, the mixing model. If they were persistently hot or persistently cold rather than intermittently hot and cold, would be really different in the response.
Yeah, so right now this correlation time is fitted to the same data that I have. So although these are ship trajectories, because they're taken, I was told that it's okay to kind of assume that the change in space to ignore the changes, but just treat them as time series and to fit of a correlation time scale on them. So what I ended up using, I think, for the heat flux is something like 60 hours. So they're pretty persistent at this stage. Yeah, it's something that we can kind of play with, I guess. But right now, these particular simulations are done with 60 hours.
So one of the concerns with any kind of fit is what happens when you get outside of the learning area. And you already addressed this to some degree, where if you get modestly outside of the area where you've learned, it seemed to do pretty well. We have experience with other things like equations of state, where you make things really accurate with a polynomial fit. And then if you have a model that's not doing so well, it can give it data that is well outside of that fit, and it behaves really badly when you have a polynomial fit. There are other functional forms which are not the case. Do neural networks inherently give you something that tends to behave better in extreme cases? Is that something that you've explored? And I raise this only because as a modeler, having things crash in less horrible ways can be sometimes useful.
Yeah, I think the behavior in extrapolation depends kind of on, it depends on the activation function you use for the neural network as well, as I was told. Yeah, for this, for at least what I looked at, the extrapolation is kind of smooth. So I wouldn't say it's terrible, but you do see that the discrepancy between ANN and core starts to get bigger when you go to more extreme temperature difference and extreme wind speed. So yeah, I don't think it will do something really crazy, but it gets less and less constrained as you go away from the training data.
Okay, Justin.
I enjoyed the talk, and what I was wondering is, when you put in your stochastic part and you had some spread, did it compare well with the scatter you showed in an early figure from a Jim Edson paper? And maybe it was answered by your animation, that animation you showed early on. Seems like maybe you were capturing the scatter quite well.
Yeah, so you mean?
Yes,
Yeah.
do you get something like that?
Yeah, so the wind stress is an easier case to visualize, and this animation is basically I did synthetic data trying to mimic the wind stress. So it is doing a reasonable job. It's a little bit harder to visualize for the heat fluxes because you will have like two principal axes, not just the wind speed, but also like temperature difference, say. So then you have to visualize things as I was showing here in this column. So you kind of have to take a slice and to pick out all these data and to see if that spread is reasonable. But like we looked at it and it seems, yeah, okay.
Right, thank you.
Any questions online? I don't think there's any hands raised or in the room. All right. Thank you, gentlemen.
Thanks.
We did 2 talks in the time it takes to do 3. This is a relaxed session. We're going to come back at the regularly scheduled time though, 2:30, and I think
Okay, good afternoon. So we sent out a survey
a month or so ago. And basically, the Wacom group created a survey, and then Ian was like, let's do a survey for MWG as well. So that's how that idea came about. And I want to present kind of an overview of what we got from as a response. So first of all, the purpose was, let's start with, it's not that we have extra resources and that's why we provide the survey. Is on the opposite side, we have very limited resource and we must allocate them strategically to best serve the community. So that was reason one for having a survey. And then it also helped us identify priority for development needs based on collective input, including interest for potential tutorials and specific model improvements. And while we value all the feedbacks, we saw all the responses and we have them recorded. The participation doesn't guarantee that we will obey specific all the requests. So when we're valuing all the input, but we must be careful how we go forward, and we're trying to be as inclusive as possible. Some things we will not be able to do, and that's it. It's important to clarify that the survey is meant to guide community-driven development, and within our resource constraint. Again, like we cannot do everything. And our goal is to align development efforts with broader community needs, ensuring that limited resources are used effectively. So I've been repeating myself the whole bullet points here, pretty much. So we had 28 participants. This is a breakdown of their institutions. So there was a lot of feedback from NCAR, but the majority of the feedback came from elsewhere, which is nice, including a few NOAA labs and universities. And also there was one international from IBS. Of those that participated, 57% are not interested in becoming a developer. And then 18% are, oh, sorry, the other way around. Yeah, 18% are, and then 21 are not, but would like to. There was one that, yes, I was. That was one an option, which was funny. Baylor is laughing, it was probably him. Of the configurations that we provided, this is how people rated them in terms of interest. It's kind of hard to see. The way we have is like you could say you're most interested, you're moderately interested, or you're least interested. And Ian and I came up with this rating. So the very high interest is in the global 2/3 and the global 1/12. Global 2 degrees, global quarter, global 136, and regional modeling all are kind of the same with moderate interest. So it's like we have the two most interested, and then everybody else is kind of moderate. In terms of science priorities behind this rating, so when we ask the question, which configurations are you most interested, we ask like based on your interest. And then we said, now that you said you classified the configurations, list your science priorities. So the one was large scale circulation and climate, so AMOC, MOC, decadal variability, heat transport. High resolution modeling, so 112 for mesoscale dynamics. And then there was also regional Antarctic modeling, ice ocean interactions, extreme events and predictability, and then the paleo climate and long-term simulation. So this is the need for the 2-degree model, and then also biogeochemistry and ecosystem dynamics. So mold water formation and BGC cycles. In terms of the development for MOM6 specifically that people would like to see, one is resolution and performance. And by the way, all these open-ended questions, the way I've used help from Google Gemini to put them together. So I basically fed all the data, said, help me make sense out of this. So and then we manually check ENI, then we capture most of the things. So just to make that clear. So MOM6 development needs, resolution and performance, so support for low and high res, regional models and GPU capability. paleo, climate, and land ice. So enhanced paleo configuration, improved ice-ocean interactions, and subair cavity modeling, physics and parameterization, refined mixing schemes, potentially overflow parameterization, and wave-driven mixing. And then diagnostics and tools, so improved post-processing, and educational diagnostics and particle tracking. And then others would be tides, regional coupling, and data documentation and analysis tutorials. We ask if people are familiar with hybrid coordinate models, and this was the response. So 50% say they are somewhat familiar, 11% very familiar, and 39% not familiar. And then a follow-up, would you like tutorials or examples materials like GitHub repositories to help better understand the vertical coordinate? And the vast majority said yes. So that's good feedback, and we'll work towards providing that. Another question was regarding a MOM6 tutorial. So we asked if people would be interested in having a tutorial in fall 2025, and 36% said yes, very interested. 43% somewhat interested, and then 21% said no. So we take it, there's a lot of interest in a MOM6 tutorial. And tomorrow we will hear from Dan Amrang when he talk about the Crocodile project updates, that there is funds, it will happen, the MOM6 tutorial fall 2025. And we would like to partner with Crocodile and also have an additional to regional stuff as part of that tutorial too. So we will do our best to make that happen this year. Then topics of interest for a MOM6 tutorial, practical applications, so model configurations with CSM, global regional, couple examples, and then customization of forcing. Data handling and analysis, so again, plotting, regrading, diagnostic packages, and budget closures. Model mechanics, so changing name lists, parameterizations, and vertical grid understanding. Development and best practice. So I'm surprised to see that people want to get engaged and learn like GitHub workflows and potentially help with development, which is great. And also they want to learn about recent development updates and tuning processes. And then finally, specific applications. So there's a fair amount of people interested in ocean ice sheet interactions and setting up MOM6 for specific concepts. In terms of biases and uncertainties to address, so this was an interesting question because we haven't released a version of MOM6 yet. So people had to answer based on experience with CSM2 or CSM1. But we made that clear in the question. So these were all the things that we got, which is great because it can help us now as we are going through tuning the model and about to release, like how are we doing in terms of all of this? So AMOC, temperature biases, Gulf Stream and North Atlantic current strength and position, mold water, deep water, overflows, the bias in salinity. I suspect it might be from someone that gave a talk this morning in the Arctic, deep ventilation, Agulhas, leakage, and mixed layer depth. So this is the summary of the survey and takeaways. So there's strong interest for a global 2/3 and 1/12 degree configuration, and then modern interest for all the other ones, 2 degrees, 1/4 degree, 136, and regional. There's a need for tutorial examples on working on native or hybrid vertical grids, high demand for a MOM6 tutorial. And then I'm not going to repeat the key biases that people would like to see improved. They are listed here again. And then finally, for us, OMWG, these are the next steps. So we will use these survey results to prioritize future model development. We would like to explore possibility for funding mechanisms and pathways based on the survey results to support key developments and community priorities. So again, we are, if anything, on the opposite. We don't have enough people here doing development and helping us make progress. So we need to find additional funding sources to make that happen. And I think this meeting is a good opportunity for us to talk about funding possibilities and how we can go after them. We will plan a MOM6 tutorial in 2025 in conjunction with Crocodile, and then address key model biases and uncertainty in upcoming efforts. So it was great to see that list, and we'll keep that in mind. And then finally, continue engaging the community for both participation and then feedback on what we have been doing. And then thank you to all of you that have participated in the survey. And if you have any other questions or comments, please feel free to email myself or Ian. Thank you.
Heard the discussion because he spoke. So go ahead, Bob.
So when people are interested in working with the hybrid coordinates, based on the comments, is it more that they're interested in working in model output in the native coordinates, or they're working with the native coordinates to be able to contribute things that would be running with the model, contributing Fortran that works in the native coordinates?
Yeah, I think it's the first one. It's like people don't understand how the vertical coordinate work, or even how to plot them the question was designed like, are you familiar, like in terms of making a plot, if I give you thicknesses instead of a Z, 1T, and I think a lot of people are not familiar with that level to begin with.
Yeah, we have had interactions where people have read a native coordinate file and it has the Z star levels as the coordinate. And then it also has the actual interface heights and thicknesses, and they're just plotting everything on the Z star levels, which is wrong. So I think it's that level of working with the output.
Yeah, partially though, the metadata is not comprehensive enough to describe that, what are the actual coordinates. It uses as the coordinates CL, and the CL is a 1D, right? So we're like, things like that are example, like if the NetCDF is self-describing, like people might be able to see and say, oh yeah, I need to use interfaces or thicknesses to make the plot. Yeah.
So of the two like fire case uses up there, like one of them has a lot of support institutionally because it's associated with the workhorse version of CESM, CMAP simulations, etc. The 112th, I mean, can you speak to directions of support and effort that might contribute to that? I mean, should that be something, is that a place where we really need a lot more resources to make progress?
I would say that on the 112, we have run a MOMS CSM with the top 110 grid for research purposes. So we know, like we have experience with that. We also now have done a few cases, regional CSM MOM6 cases at 112, and like we know what set of parameters we need to set enclosure and so on and so forth. We have the grid for the 112. We have the topography. We've done like 5-day runs. It's just a matter of like, when the time comes and say, we need to put that together, we can do it, I think, very efficiently. But I'm hoping it always takes more than what we say. But that's one thing. But then is not to evaluate that, to then validate and tune that. I think that's another can of worms. I see that one kind of pop. Now we're seeing what Fred presented today. How long did it take for the ocean section to put and others to put that together? Many years. So it's hard to say. I think to answer your question, and we are ready to get going now, but like we need additional resources to help us, go to the next level, evaluate the simulations.
On the 1/12th of a degree, that's the same resolution that is used operationally for the real-time ocean forecast system and other things. And even though the scientific applications could not be more different, there's a lot of kind of the technical stuff that you just kind of have to grind through, where there might be some strong synergies where this configuration is something which could be done with less resources than if you were trying to do it all on your own. And I know for a fact that folks at EMC would be interested in sharing things where there's actually common challenges you're dealing with. And there are plenty of common challenges as you push to that higher resolution with moving around data volumes and setting up the grid in the first place, making sure that you're using geocentric latitude instead of geodetic latitude for your land sea masks and other things.
Are we, Frank?
No idea. So, yeah, speaking off the cuff, because we haven't digested and made plans yet, but I think those two the two top ones are priorities for our own internal limited resources. And then, of course, some of our internal limited resources can be allocated to the other things, but it's probably the other things that would need more external support.
Yeah, so the 2 degree, we've had help from external collaborator, and again, is in the same boat, like we're ready to go, like if we need, in terms of get the model running, but then in terms of tuning, evaluating tuning, that will take some time, and we don't have the manpower in-house to do it.
One other thought, there was a kind of a medium priority for a high resolution Pan-Antarctic configuration. The natural synergy there would seem to me to be with the COSMA group in Australia, who's actively using MOM6 to address a lot of the issues that you would need to. And so again, finding partnerships and synergies. And I think that's a good group. There were a large handful of people who came to the Commodore workshop last September, and I suspect you would find an awful lot of interest.
Yeah, and we've been in touch with them already, and through the Crocodile, and yeah, Adele is leading that, so. Thanks, Paul.
Yeah, I was just gonna, well, relating to our waves conversation we were just having, it would be, I recognize that the manpower is really limited here at the moment. Going forward, it would be helpful if you were prioritizing sort of enabling collaborators with that power, rather than trying to do all of the pieces yourself and saying, as soon as we get this done, then we'll be able to have, accept your help. Because I think there are a lot of groups out there who would be happy to help on specific issues that they have expertise in, if that's sort of the protocol and the approach and going, and I recognize that's complicated to figure out, but that has not seemed to be prioritized in the last year or so. And so we would have been happy to help in numerous occasions in the last year.
Yeah, no, I understand, and thanks for bringing that up. And no, up to very recently, the way we've been operating is, Lab C froze. We need to devote our attention to fix this. And then, now we have the boy PCC, it's a showstopper, we have to, so it's always like, we can never have enough time to think about this, and even I think to do what you're talking about, we need ourselves a workflow that we can then provide to you. And I feel confident that we are now getting very close to that. So we can, again, as we talked before, we can work together, and if you just follow what we've been doing, you'll get part of the whole CSM evaluation now, not just in the ocean, but if you do couple, then other people will look at the results as well. So I think we're very close to do that, and I think it's a great point that you made. We are ready for that phase. Yeah.
Gustavo, though, I think it really means we'll be ready for that when we replace the science liaison position. Right now, the Ocean Working Group does not have a science liaison to provide exactly that sort of interface to the community. And you're fulfilling that role, but you also have a lot of other stuff on your plate at the same time.
Yeah,
and
that's for sure. Yeah, I agree. But we don't know if that's going to happen or not. If that we had the position open,
we're in right now.
Yeah, but
Staffing is
regardless,
just small, it's decreasing.
Yeah, but right now we got in a momentum where it's not just me running the model, other people are running, and we have a framework that we follow through. And I think that framework that Taylor and others can use to come in and before, people were doing their own runs, or that you would do. Now we at least have a protocol, mostly because we're following through with the rest of the CSM development. So, yeah. Thanks for the.
Just to make that explicit for this community, I think maybe it's worth people knowing that role, is not filled right now. The person who's going to primarily interface with the community and be ingesting new technologies. That hire is on hold. So, you know, insofar as we can all prioritize the importance of that in our interactions, that's something that's really important for us to move forward.
All right, I'm gonna wrap it up actually, so we can stay on time. We can keep having these conversations through the rest of the workshop, but I do want to get to the next speaker, who is Jun Yu. So the slides that you had up a minute ago.
Yeah, hello, can you hear me?
Yes, we can hear you.
Yeah, cool. Let me share the slide. Can everyone see my slide?
You can see it.
Okay, cool.
Yep. Full screen.
Okay. So hello everyone. My name is Jin Yu, and I'm a fourth-year PhD student in UC Irvine, and I'm working with Professor Keith Moore. So today I'm gonna present the first chapter of my PhD work, which is a deep collaboration with NCAR's CSM2 Marble team. So this work is about expanding the marine ecosystem in CSM2 from a standard 3 types of phytoplankton and 1 type zooplankton to 8 types of phytoplankton and 4 types of zooplankton. So currently this work is on the review on James, and we believe this is the next generation marine ecosystem model with the potential to capture the future ecological shifts that will drive ocean biogeochemistry with climate change. So first, let me start with the big picture of why we need to do this. So the biological pump plays a critical role in storing carbon from the atmosphere. So efficiency of the biological pump is largely modulated by the composition of the ecosystem community. So as we can see in this figure, in the stratified oligotrophic regions such as subtropical oceans, the ecosystem there is dominated by smaller size phytoplankton and smaller size zooplankton. So as a result, the efficiency of the biological pump is weaker. By contrast, in the region with upwelling and nutrient-rich ecosystem, the ecosystem is normally dominated by larger size phytoplankton and larger size zooplankton. So the efficiency of the biological pump is stronger. But when we look at the future warming scenarios, so we can expect that the expansion of the oligotrophic condition to expand like globally, and it will lead to the ecosystem shift in the nutrient-rich regions from the larger size phytoplankton to a smaller size community. So it will cause a cascading effect both on the ocean biogeochemistry and also on the higher trophic levels. Therefore, it's critical to assess how ecosystem will shift in the future warming scenarios and how that will drive ocean biogeochemistry with climate change. So to eventually answer these questions, we need a marine ecosystem model that has more realistic representation of complex ecosystem processes and symbologies. So here we build this new biogeochemical model on Marble with expanded ecosystem to 8 types of phytoplankton and 4 types of zooplankton. So we call it AP4Z model. So this figure shows the food web structure of the AP4Z model. So for phytoplankton, we have include pico-size, nano-size, and micro-size phytoplankton. So for pico-size, we include Prochococcus, Psittacoccus, picoeucaryotes, and diastrophes. So these phytoplankton is important in always dominant in the oligotrophic subtropical oceans. And for nano-size, we have a Coccolithophores, Biodesicus, and other nano phytoplankton. And for micro-size phytoplankton, we include diatoms as the classic representatives. Besides these primary producers, we also include 4 different types of secondary producers. So we have a small microzooplankton as the main grazers for the smaller sized phytoplankton, and also large microzooplankton as the main grazers for the pico-size and nano-size, and mesozooplankton are the main grazers for the larger size phytoplankton and also the large microzooplankton. And finally, the macrozooplankton are the main grazers for diatoms and the mesozooplankton. So this model to mention that the larger size zooplankton are the main food source for the fisheries. So this model has the potential to link with fish model and predict the future fishery yields. So when you look at this model structure, you may notice this have this complicated food web structure here. So the principle of assigning this grazing relationship is we following the optimum predator to prey size ratio. So for example, the size of this zooplankton is about 2 to 20 micrometer, and the size of the most preferred food is about 10 times smaller than that. So basically, we follow this optimum predator to prey size ratio. We assign the grazing relationship in that in the model. Finally, we wanted to show some tuning results under the current time forcing. So we first examine how well the Marble AP4Z model does at stimulating the broad biogeochemical fields, such as nutrients distribution and the key biogeochemical fluxes. So these are the standard metrics typically used to evaluate the ocean biogeochemical component in ESMs. So first we're looking at is the model data comparison of the surface nutrient distribution here. So as you can see, the model captured the general patterns and also the magnitude of the nitrate and phosphate and silicate. So they are all in good agreement with the observation. A figure on the right is the model surface dissolved iron distribution and compare with the data set. So the model also capture the spatial pattern and the magnitude of the dissolved iron globally. Besides the surface distribution, we also look at the vertical distribution. So figure here shows the vertical profile of the global averaged nutrient distribution of nitrate, phosphate, and silicate, and compare with the observation. So as you can see, model accurately capture the vertical variability of these key nutrients, showing really high R values, like higher than 0.9. Also, we pick one depth of 500 meters to show the spatial patterns and compare with the data set. And the model also did a good job on capturing the spatial pattern and variability of nitrate, dissolved oxygen, N-star and silica star compared with the observations. And then we picked two ocean regions. One is the Atlantic Ocean and one is the Pacific Ocean. And we look at the vertical profile, compare with the model compare with the observation. So as the figure shows, the model also capture the vertical variation both in both ocean regions, show really high correlation values for all three key nutrients. And next, we check how well the model does on simulating the key biogeochemical fluxes. So we first compare the model MPP with satellite MPP, and it shows in good agreement in terms of the spatial pattern and also magnitude. And then we look at the latitudinal variation and also the seasonal variation. The model also capture such variations, showing good agreement with the observation. And then we compare other key fluxes, such as a PLC flux, export ratio, calcium carbonate fluxes, and silica fluxes. So, and we compare our model, the PLC flux, with satellite-based data. So both model and satellite shows higher PLC flux in the nutrient-rich regions and relatively lower in the subtropical region. And the model also showed a great similarity between the modeled export ratio and the satellite derived export ratio here. And then we check all the key fluxes as a global integral, and our model shows that the total fluxes showed a good agreement with the observation, both in terms of MPP, fixation, POC flux, and also the global mean export ratio, calcium carbonate flux, and the silica flux. Next, we want to checked the modeled phytoplankton biomass compared with the observation. So this figure shows the comparison between the observation of the pico-sized phytoplankton, and here is the model performance. And figure on the right is observed larger size phytoplankton, and figure on here is the model of larger size phytoplankton biomass. So overall, the model can generally capture the large scale spatial patterns, and also generally within the magnitude. So both the model and observation show that Prochycacus is a dominant species in the subtropical ocean, and the larger size phytoplankton and the nanophytoplankton are co-dominating in the higher latitude. So we want to point out that the observational data is kind of sparse and also have subject to large uncertainties related to cell counts and conversion to of cell abundance to biomass. So we further validated our model biomass by comparing satellites. So satellite provides the estimates of phytoplankton biomass for three size classes: pico size, nano size, and micro size. So we compared the percentage relative to the total biomass. As you can see, the model reproduced the spatial pattern and also the magnitude for the three size classes. Both of them are showing like dominance for the pico size phytoplankton in the subtropical gyre, and co-dominance for the nano size phytoplankton and micro size phytoplankton in the higher latitude. And also we average the data over the we average the zonal mean, and we can show that the model also reproduce the latitudinal variation for the three size phytoplankton. And then we look further checking the zooplankton biomass. As you can see, the model can capture the spatial pattern of the observed zooplankton biomass, especially for the mesozooplankton, because there's a lot of there's a large spatial coverage for this zooplankton. And then we further check the seasonal variation, and our model can generally capture the seasonal variation for the mesozooplankton when we compare with the observation, showing like higher biomass in spring and summer in the high latitude, and relatively lower in the fall and the winter. Next, we checked how well the energy flow along the food web, and that will indicate whether the grazing relationship we assign in the model is reasonable. So our model estimate that microzooplankton consume about like 55% of the MPP, and have the highest value in the subtropical gyre and relatively lower in the subpolar regions. And all these values kind of consistent with the field data suggest. And our model also produced mesozooplankton consume about 20% of the MPP, and the left about 5.5% of MPP consumed by macrozooplankton. And finally, we want to use this figure to show whether the model has the potential to capture the future ecological shift. So figure on here on the left is we choose a box in the North Pacific subtropical, and figure on the right is the box we choose in North Pacific subtropical. So in the subarctic region, there's a seasonal variation of the available light availability. We can see the light increase from winter to spring, and then decrease from summer to fall. And for the key species there, the diatom, you can see the biomass increase from winter to spring when light increases, but it can decrease sharply from spring to summer. And that is because the grazing pressure is increasing when during the spring and summer. So that will cause the biomass to go down. And the carbon export generally follows the pattern of the mesozooplankton biomass. So this finding is supported by the comparing the zooplankton biomass with the observation. So both the model kind of reproduced the similar seasonal variation compared with the observation. Indicating the model has potential to capture the future ecological shift, responding to the change of physical condition. And figure on the right is the comparing. I just want to show the relationship between the surface nitrate and the Prochycacus. So as you can see in the subtropical region, in winter there's strong mixing and cause the higher nutrients in there, and during spring, so the Procalcacus carbon is kind of lower in here, but when during the summer and fall, when the strong stratification happen, the nutrient availability going down, but the Procalcacus percentage is going higher because they can adapt to extremely low nutrient condition. So this result highlights the importance of Procalcacus in the model that will dominate in the future warming scenarios. And Mr. zooplankton biomass kind of like stable, have less seasonal variation, and POC flux kind of resemble the microzooplankton seasonal variation. Finally, there's some key takeaway from this study. So we developed a next generation marine biogeochemical model with the expanded ecosystem in CN2 marble, with the ability to model the key species that's being observed in the ocean. And then the AP4Z model generally reproduced the observed phytoplankton and zooplankton community composition with a good performance of simulating broad biogeochemical fields. And finally, the model simulates reasonable energy transfers through the food web with the potential to capture future ecological shift that drives the marine biogeochemistry. Thank you.
Questions in the room or online? I can start with a question. You may have mentioned this, I may have missed it, but on your slide showing net primary production in OBS in the model, it looked like there was the model has these excess primary production in the North Pacific and North Atlantic. I wonder if you could explain that.
Yeah, that's a good question. So we think there is there's a mismatch between the atmospheric forcing and the ocean in terms of the location of Crucial and the Gulf Stream. So it causes like artificial strong mixing over there. So that's why the model have this weird like a higher MPP in here compared with the satellite.
So is it, do you think because of bias in the model and the position of the currents?
Yeah, there's a mismatch between the forcing and the ocean, the pole.
Okay. Frank.
So I understand that there's interest in having a finer granularity information about the ecosystem composition. But in terms of the net properties of the system, like NPP or net particulate flux, is this model an improvement over the standard marble formulation?
Oh, that's also a good question. It just because we are now running the model under the current climate forcing, and all the models are tuned to get the NPP to match all the observation, right? So it's kind of hard to say which model is better because we're all tuning that way. But I think that the interesting thing is when you run it to the future, so the different feedback on the ecosystem will start show up. And then I think that's when we can compare what's the missing feedback between the simple ecosystem and more complicated ecosystem.
Thank you.
I hope that will answer your question.
Thank you. Other questions? In the room or online? All right. Thank you again. Can you? Your last speaker. Okay.
Hello, everyone. My name is Kazuhiro Misumi. I'm from ClearP. That is a non-profit organization founded by Japanese power companies. So I'm belonging to the organization related to power companies. So we are investigating artificial radionuclide in the ocean. And this study is ongoing and in collaboration with Keith Lindsay and Frank O'Brien. And I'd like to talk about the implementation of artificial radionuclide in CSM2. Artificial radionuclides serve as a variable tracers for evaluating ocean model performance. Their source terms are relatively well constrained, making them efficient validation tools. Unlike natural radionuclides, they provide a clear temporal evolution from their initial state, enabling assessment of model transient response. So target actual radionuclide in this study is cesium and plutonium isotopes. And cesium-137 has a relatively short half-life, and it has relatively low affinity to sinking particles. The affinity of to the sinking particles can be represented as a Kp value, that is distribution coefficient. The value is roughly 10 to the power of 3 for cesium. That is relatively low value for the radionuclides, so it has a low affinity to sinking particles. So this nuclide is a good proxy for water mass movement. On the other hand, plutonium isotopes has a long half-lives, and it has a modest affinity to sinking particles. The Kp value is 10 to the power of 5, and this nuclide is a good proxy for particle scavenging. And both artificial radionuclides are supplied to the ocean mainly by the global fallout due to nuclear testing. And this is a horizontal distribution of global fallout for cesium 137, deposition rate in the log scale. And we can see higher deposition rate in the northern hemisphere. This is because atmospheric nuclear testing were mainly conducted in the northern hemisphere. And lower panel shows a temporal evolution of the deposition rate for cesium in blue and plutonium for orange. And we can see deposition starting from 1945 and gradually increasing, but note that it is in log scale towards the mid-1960s, and then gradually decreasing. This is because partial test ban treaty effective. And for the temporal variation of the plutonium, this is a basically mirror image of the cesium deposition rate, but a factor of 0.01. And this temporal variation is coming from this specific area. There are other sources important for these radionuclides. For example, discharge from nuclear reprocessing facilities and closing fallout from Pacific nuclear test site. But these other sources are not included in our simulation currently, so this is at least out of scope in this talk. And this is observed data for cesium and plutonium. Cesium in the upper panels and plutonium for the lower panels, and 60s and 90s and 80s. And we can see high cesium and plutonium concentration in the surface water. In this period, this is because the high deposition rate in the 60s. And then we see the gradual decrease towards the 80s like this, both nuclides. And we can see very high concentration around here, but these are coming from nuclear reprocessing plant. So this is out of scope in this talk. We mainly focus on the radionuclide in the North Pacific Ocean. And it is important to note that the color scale is for the plutonium is a factor of 0.001, despite the forcing term is a factor of 0.01, meaning that the plutonium is rapidly removed in the surface water. And this figure shows a vertical profile of cesium and plutonium averaged over this red colored area. And we can see high cesium concentration in the surface water. And we see the modest values in thermocline, but the cesium concentration are very low in the deep ocean. On the other hand, for the plutonium, we can see very, very low surface water in the surface water, but it increases in the thermocline, and also we can see higher concentration, especially in the later period in the deep ocean. So despite similar external forcings, the particle profiles are very, very different, suggesting particle-mediated transport for the plutonium. If we put spline interpolation in this figure, maybe we can see some descending of the maximum concentration depth like this. But these lines are arbitrary, so it is worthwhile to investigate the different behavior using numerical model. So the purpose of this study is try incorporating the artificial radionuclide module into CSM2 to reproduce the different behavior of the cesium-137 and plutonium isotopes. The model we are using CSM 2.1.5 and the composite is D1850 ECO. That is combination of two CIC5 and MARBL. And there are several caveats. We are starting from the default initial condition, no spin up. And the simulation is for the 1945 to 2006 with changing radionuclide deposition rates, but post with a normal year forcing. So there are no internal variability in this simulation. So we are planning to redo this simulation with appropriate initial and boundary conditions. The radionuclide model uses the somewhat old model. This model is originally developed to investigate protoactinium thorium ratio. And this ratio is used as a proxy for AMOC in a paleoclimate study. Briefly, the feature of the model is a prognostic variable is a total amount. That means that sum of dissolved and particulate phases of radionuclide. And the model diagnoses the dissolved and particulate fractions, assuming instantaneous equilibrium in model grid cells using a distribution coefficient Kp. And here's more detail. The prognostic variable is a total radionuclide. And this is a nuclide I. This is the sum of the dissolved and the particulate phase. And this is a prognostic equation. Tendency is calculated by the sum of the transport term and the source term. This is a global fallout in this study, and radioactive decay and gravitational settling. And this is only applied to this particulate phase. The partitioning between this dissolved and the particulate phase is calculated by this distribution coefficient that is defined by the nuclide in the ratio of nuclide existing in the particles normalized by the particle density to the nuclide in the dissolved phase, water, normalized by the water densities. And if we introduce the Cp value defined as a particle density divided by water density, we can get this relationship. And this Cp value is basically representing the abundance of particle because the water densities changes in water density in seawater is usually less than 1%. So, but the particle density is significantly different depending on the ocean environment. And now we can obtain this relationship from this equation and substitute this into this equation and solve it for dissolved phase. We can obtain this relationship. And this is a prognostic variable. And this distribution coefficient is a kind of experimental value. So their IAEA value provide a recommended Kp value for the various radionuclide. And this Cp representing the particle abundance can be diagnosed from the MARBL output. So we can obtain dissolved phase from the prognostic variable like this. And then we can obtain particulate phase from this relationship, and we can evaluate this term. So we can close the equation. And there are various types of particles in the ocean, for example, aeolian dust and organic carbon and calcium carbonate and opal. And if different types of particles do not interact with each other, then the effect can be expressed as this kind of linear combination. And we can obtain this C dust value, for example. MARBL diagnoses dust flux, and if we assume the sinking velocity of dust, then we can obtain dust particle density in the model grid cell. And we can put this into this definition, and we can obtain the C dust value. This is coming from the equation of the state. And we can obtain all of these C values from the model. In this study, but however, we assume a simple parameter. We are assuming the single thinking velocity of particles, 1,000 meter per year, and a single distribution coefficient, all the types of particles. This is just for simplicity. This is a first step, so we'd like to make simple as possible in this simulation. And we conducted 6 cases targeting on cesium and plutonium. For the cesium mid case and plutonium mid case, we used Kp value from the IAEA reference value. And we conducted sensitivity experiment lower and higher cases. For cesium low case, we used Kp value is equal to 0. This is very simplified approach because if we put Kp is equal to 0 to this equation, then the total radionuclides are all in the dissolved phase. So we do not need a particle concentration for this simulation. And also for the plutonium, we conducted sensitivity experiments like this, 1 order of magnitude difference. Now we see the result for the cesium mid case. This is a horizontal distribution of cesium for the surface water and 25.5 sigma theta. This is the density level of the motor water in the Pacific Ocean. And here's a 60 and 65 and 70. And we can see significant increase in the surface concentration in the 65 and then decrease towards the 70. And we can also see some intrusion into the subsurface, subducted to the subsurface and transported isopically in the as a mode water like this. So there are east to west propagation in this density range. Now we compare the vertical profile along this 165 line. Here is a vertical profile of the cesium concentration along this line. Here's the north and the south, and here's the depth. Again, these lines representing the mode water density range. And we can see high cesium concentration in the surface water, 1963. But it penetrated, subducted in the subsurface and transported isopically as a mode water, and then they accumulate in subsurface layer like this. We can see local maximum around here, 2002. And we have observed data for this section in the 2002. We can see high cesium concentration density levels of 25.5 and 26.0 mode water density range at the 20 degrees north. And we can see local maximum similar density levels and also 20 degrees north. So I think the model did a good job to reproduce the cesium concentration along this line. But somewhat the concentrations are higher and the density structure are shallower compared with observed data. Now we move on the difference among the cases. But we are using different value for Kp for all the cases, but we cannot see the difference among the cases. So this is good information because using Kp is equal to 0 is a very good approximation for simulating the cesium. Next, we move on the plutonium. Here is a plutonium concentration in the surface and also to 25.5 sigma theta, 60, 65, and 70. And we can see again see the high concentration in 65, and we can see some subduction to the subsurface. Very similar response compared with the cesium. Now we compare this vertical profile. Yeah, and again, we can see the very similar distribution for plutonium, but we can also see the local maximum around here. But position is somewhat different compared with the cesium, like this. Cesium is located around here, and plutonium we can see somewhat deeper and shifting northward like this. Now we move on the comparison among the cases for the plutonium. We can see very different result for in this case. And for the plutonium low case, we can see very similar response as the cesium. At first, it is very low and increase in the surface water, and then accumulated to the subsurface as a mold water and gradually decreasing like this. For the plutonium mid case, we can see somewhat descending of the maximum concentration compared with this low case. And the plutonium high case, we can now see the significant descending of the maximum concentration like this. So the results are so different, and something change around this parameter space. And this is a plutonium high case, vertical cross section along the 165 degrees east. And note that the depth scale is now 3,000 meter. Previous ones are 1,000 meter. And we can see significant descending relative to the isopiconos. And we can see, so this now the isopiconal transport is not important for this simulation. And we can also see much faster sinking of radionuclides in the mid to high latitude. This is because of high biological production in the mid to high latitude. It increases biogenic particle a lot, and it results in faster sinking in this higher latitude. So here's a summary. Our particle-mediated transport shows varying significance with Kp. Negligible at Kp is 10 to the power 4, becoming apparent at 5 and prominent at 6. For cesium-137, where Kp is expected to be around 10 to the power 4 or less, setting Kp is equal to 0 serve as a good approximation, so allowing a simplified calculation. For plutonium, observed data showed qualitatively similar behavior to high Kp range. And the differences in vertical transport seen in observed data could be explained by the differences in Kp based on the literature values. So here is future directions, and that's all. Thank you very much. Question.
So when you showed the observed data, it looked like the higher concentrations were on the western side of the Pacific, and the model is very clearly on the eastern side of the Pacific. Maybe the sampling was quite sparse, but I was just trying to think which process is which. So like in the 70s here, it's much stronger on the, so maybe it's not so bad. It's the sampling pattern is much stronger in the west rather than the colors.
Are you looking at this one?
Yeah, so
Oh, sorry. This one?
yes, that one or the next one next to it.
Okay. I think in the surface water, cesium accumulated in eastern border like this because of surface current transports the cesium deposition rate is maximum at 9063. So the surface transport accumulated into this kind of stagnant gas.
Good, Frank. So pragmatically, I mean, the idea here is to use the difference between these two to help constrain the particle transport processes as well. So the observations here, the observations here are pretty sparse, subsurface observations of both isotopes. And there's a fair bit of uncertainty in this affinity parameter. Do you think this data is really up to the task? I mean, relative to, say, sediment trap data, being able to constrain the particle fluxes, is this really going to be able to add information to our understanding of or being able to have something to tune the particle representation in the model.
Yeah, this data is very sparse, but I think we can obtain some information. For example, in this case, the subarctic area shows a very high, rapid decrease in the subarctic area. So we can see the spatial pattern that is very difficult from the observed data. Maybe we can see some information about it. And also, I realized that the particle concentration in this simulation is very important because if we transfer this dp value in the left side, then the product of Cp and Kp, if this value is equal to 1, then the AP and AD is a half and half. So this kind of threshold showing the different behavior. So this value is very important. So we need to check the particle flux simulated in the model, and maybe we need to compare that with the observed data. Maybe sediment trap or something.
That's not an oceanographic question, but a human health question. So your surface concentrations that look like peaked in the cesium, like 40 becquerels per cubic meter and 0.1 for plutonium. What's considered the threshold for safety for consumption of fish?
I'm a beginner. I'm not pretty sure, but I think this is not so bad for human health in this concentration level, I believe. And now is the concentration much lower than the disease value, so I think it is no problem.
Just the tuna we ate in 1965 is a problem.
Respond to Frank's question about the sparsity of the data. I mean, coming from a paleo oceanographic perspective, this is amazing.
Yeah, I know.
So, but I mean, like, why do we think we can get away with constraining some of these things? Well, I think it's because we think that the length scales of tracers in the intermediate and depth deep ocean are relatively long. I guess the question is, in some of these paleo studies, people have posed a kind of formal inverse problem, often using matrix advection approaches, which can really speed up the way that the tracers are distributed, and then try to infer things about the distribution of mixings. I mean, here your sources and sinks, like you say, are well known. So is that part of your research program, or are you trying to leverage any of these like rapid, like offline advection type tools?
Yeah, maybe it is some, data is related to the forcing data, it's a high uncertainty, and I think such kinds of approach is very useful because this model is very simple, but there are a lot of unknown parameters like this. We do not know much about which one has a high KP, so testing using such kind of tool is a good approach, I think.
One difference here is that the interest here is in the transient problem, not the equilibrium state. So
Yeah, but although folks have tackled that in the paleo context too, where often you're interested in the rate of flow and you need some kind of clock, and that can come from protactinium or radiocarbon. So.
Good, thanks again. And I think that's it. We've got one more though.
Yeah, I'll have a little break and then the last one.
Yeah. So break until so 15 minutes break till 4, and then just one more talk at 4. Sticking around for the last time. Last question. Are you ready?
Yeah.
All right, go ahead.
Thank you everyone for showing up, and thank you everyone for showing up online as well. I'm Jiang Zhu from the Paleo group at NCAR, This work is done with Betty Otto Gleisner, Sofia Markowicz at the Paleo Group. And also I received a lot of help from Ian, Gustavo, Alper, and Gorka. A quick introduction about the last glacial maximum. It's a ice age climate. It's very cold. On average, the global temperature is 6 degrees C colder. And on the left, we have a visualization of the surface air temperature change. And you see it's very cold. And you can also see the big ice sheets cover a big chunk of the North America. And from forcing feedback perspective, this cooling is caused by lower greenhouse gas and expanded ice sheets. Why should we care about the last glacial maximum? Well, one straightforward application is that we can use that to assess model climate sensitivity. This is an old idea dated back to Manabe and Broccoli, 1985. And in their study, they attempted to use LGM to assess 2 different versions of the GFDL model with different cloud parameterizations. And the figure on the left, my side, it's a summary of the work happened over the Paleo Group over the past few decades. And it's a summary of the equilibrium climate sensitivity against the global cooling at the LGM. And the dots are different CSM models from the early days, CSM1 all the way to CSM2. You see a very nice relationship between them. And the higher the climate sensitivity, the colder the LGM is simulated in the model. And again, the nice thing about the Paleo is we have real world information about how cold the LGM was. And in this case, we are using Tierney 2020 as a constraint. And based on that, we can see CSM2 with a high ECS, which simulates an LGM cooling of 12 degrees C. It is way outside the geological evidence suggested range. So suggesting that the high ECS is unrealistic. We can take one step further and to use Paleo data to examine the details of the parameterizations. And in this case, we identified issues in the microphysics and ice nucleation scheme. After correcting those issues, we developed the paleoclimate calibrated CSM2 in blue. And you can see the LGM is much more realistic and the ECS is also much lower. So once we have a global climate that we are happy with, then we can start to look at other aspects of the climate system. For example, the AMOC, Atlantic Meridional Overturning Circulation, which arguably is one of the most important ocean circulation system in the climate system. So the figure on the left is from a seminal paper, Curry and Opel 2005. They try to summarize the carbon-13 information for modern ocean and the glacial ocean, last glacial maximum. And you can think this tracer as a water mass tracer. For example, over the North Atlantic, the high values is thought to be related to the North Atlantic deep water. If you look at the glacial climate, you see that very clearly the North Atlantic, the Atlantic bottom ocean is passed by the southern south water, so with very low values. And their original interpretation was that AMOC must be very shallower than the modern ocean. And this idea has been supported by many following studies. So basically the current consensus is that the AMOC was shallower at the LGM. And the strength, some people believe it's weaker, other people think it's not well constrained. So it's hard to say. Why the AMOC was shallower at the LGM? Here is a diagram from a paper by Ferrari 2014. they provide a very elegant theory about this shallowing AMOC. So starting from the plot on the top, the red here is the isopacinal surface over the southern ocean, and the slope is determined by wind stress and mesoscale eddy. And for the water mass upwelled to the south of the isopacinal surface, it will lose buoyancy because of brine rejection underneath the sea ice. For the water mass upwelled to the north of the isopacinal surface, they will gain buoyancy because of melting of sea ice and atmospheric heating. And you can see that there's a close coupling between the ocean dynamics, circulation, and the sea ice fraction. And for LGM, it's a colder climate. Both model and proxy suggest much expanded sea ice. As a result, that will impact the ocean circulation. So the basic idea is that once we know the slope, again, it's determined by mesoscale eddy and wind stress, and we know the ice extent, we can compute the depth of the isopacinal surface here. And for LGM, if you make assumption, all the others stay the same, except for the sea ice cover, you can very easily say that the sea ice expansion will make the isopacinal depth shallower. So I like this theory a lot because it's very simple. Of course, if you look at the real world or what's happening in the model, a lot of things are changing. So it may be complicated, should be complicated than this. And this theory is elegant. It constrains the depth of the AMOC, but does not necessarily constrain the strength of the AMOC. There are other studies focusing on the North Atlantic forcing, trying to say that maybe the glacial ice sheets can impact the surface wind pattern, which can impact the salt transport over the North Atlantic. They may also impact the sea ice distribution over the subpolar North Atlantic. That will impact the AMOC as well. Can models simulate the shallower glacial AMOC? It is really interesting to note that CSMs are the only PMAP3, PMAP4 models that can simulate a shallower glacial AMOC. So there are a lot of plots here, but maybe just focus on the highlighted red boxes. So we have CCSM4, CESM1, and the altered version of CCSM4. So those are the only models that can simulate a shallower AMOC. So there are maybe a couple reasons that why the other models cannot simulate a shallower AMOC. One reason could potentially be that people need to run the LGM simulation longer to let the deep ocean, southern ocean to evolve. It could also be due to that the other models, they do not do a good job in simulating the southern ocean processes, including the coupling with sea ice. So with that background, the goal of this study is to perform LGM simulation using CSM3 with MOM6 to assess climate sensitivity and AMOC. So we use CSM3 beta 04. It's not the most recent configuration, so it's around 121 setup. The boundary condition includes lower CO2 and the presence of LGM ice sheets. So basically higher albedo, higher topography, altered surface properties, and the lower sea level. And we use CSM4 LGM as an initial condition to spin up the CESM3 LGM because the model is expensive to run, it's slow as well. During this process, we developed a suite of notebooks. It's available on GitHub. And I also want to give a big shout out to Alper, who developed the MOM6 BASI. It's very easy to use, so made our life much easier. So thank you for that. And thank you, Ian, for providing us multiple versions of the HYCOM vertical coordinate density targets. So we are able to test the sensitivity to that as well. Next, let's look at the results, starting from the global mean surface temperature. The thicker lines are the LGM simulation. So blue is CESM3, red is CESM2. And you can see that after initialization, after 100 years, CESM3 is already 2 degrees C, more than 2 degrees C warmer than CESM2. This is really good news for us. We know that CESM2 is too cold. And we can put this into a bigger context. And so based on this preliminary simulation, we think CESM3, the LGM might be somewhere right in the middle of the geological evidence-based estimation, and the sensitivity is much lower. So this is really great news for us. Next, let's look at the AMOC. The bottom panel on the left shows the AMOC for the LGM. And clearly it's much shallower, maybe by 1 kilometer, and the strength is much weaker, maybe by more than 40%. So if we believe this published recent paper, this is in excellent agreement. But I'm a little bit worried about this weakening trend. So initially, it's pretty dramatic weakening, and then we still have a small weakening trend. So we need longer simulation to have better assessment. Hope the AMOC is stable, because if the AMOC collapses, it won't be, it's hard to reconcile with paleo data. Put this into a bigger context as well. So we are looking at AMOC across different CESM model versions, starting here from CCSM3 all the way to CESM3. So the dashed line in the bottom panel shows the zero contour of the AMOC in the pre-industrial simulation. So the message to highlight that all the CESM simulations show shallower glacial AMOC, so that's nice. And if you look at the strengths, maybe CCSM3 and CESM3 are the two models that stand out with very weak glacial AMOC. So one explanation could be that because in those two models, we don't have overflow parameterization. If we can have that, maybe the AMOC might be stronger. So that's what we see in the middle columns of the simulations. They all have overflow parameterization. This could also just be a coincidence, so it's hard to say at this stage. An alternative explanation could be because the winds pattern may be different, the sea ice expansion is different, so it will impact the deep water formation in the North Atlantic. Okay, move on. This is our first time to use MOM6 in paleo, and this is our first time to use the hybrid vertical coordinates as well. So we want to carefully examine the influence. So here we are comparing two simulations. The only difference is the vertical coordinates. The bottom is the star, the top is HICOM vertical coordinates. We also have the time series of the maximum AMOC over the northern hemisphere, and also the transport at the southern tip of the Atlantic. So based on this metric, the AMOC might be slightly weaker by maybe 1 or 2 swirl drop in the Z-star vertical coordinates. My naive interpretation at this stage is that maybe in the HICOM simulation, we have higher effective vertical resolution, which can better simulate the deep water formation process. We can also look at the mixed layer depths. The lower right plot is the sensitivity to the different vertical coordinates. You see that it's not small. I'm only looking at the LGM right now. It's not small, so over the subpolar North Atlantic, it could be a couple hundreds of meters. And over the Southern Ocean, Weddell Sea, and the Ross Sea, the sensitivity is much bigger. By the way, I want to quickly go through the LGM as well. You can see that because of the colder climate bigger sea ice expansion in both hemispheres. So over the southern hemisphere, we have the brine rejection that wins, we have deeper convection. Over the northern hemisphere, the sea ice insulating effect wins, so we see a suppression of convection. Next, let's look at temperature. So global mean surface temperature first. There's very small sensitivity to the choices of the vertical coordinates. So Z star is slightly colder. And if you look at the global mean ocean temperature, maybe this is a bigger difference. So the difference is 0.05 degrees C in global ocean after 100 years. So my current interpretation is that maybe the trend is greater in the simulation with Z star coordinates. Maybe this is due to the more spurious mixing in the Z star coordinate simulation. Thanks to Ian, I got multiple versions of the density targets for the hybrid vertical coordinates. So I tested the sensitivity to that as well. So you compare the blue and the red. I only have 50 years right now. Overall, if you look at AMOC transport, the sensitivity is not that big. However, if you look at the mixed layer depths over the subpolar North Atlantic, the newer version of the density targets produce deeper, maybe stronger deep water formation. And we do see a very big sensitivity over the Southern Ocean, Weddell Sea, and the Ross Sea. So I don't know what's going on there. Okay, I want to switch gear and use the next few minutes to talk about what we would like to do beyond the LGM. So here is a slide trying to summarize the finished and ongoing work using CSM1 in paleoclimate studies. So the time series are the global mean surface temperature over the past 500 million years. And the pictures are the early career researchers, PhD students, postdocs, whose thesis and postdoc work used CSM, and their photos are aligned to the time periods they are working on. So for example, Sophia is our colleague at Paleo Group. Her PhD thesis used CSM1 to simulate the Carboniferous glacial interglacial climate. And take myself as an example, my PhD thesis used CSM1 to look at ENSO variability at the last glacial maximum and the water isotopes. My postdoc work used CSM1 to look at the extreme warm greenhouse climate. And we also have very wide international users of CSM1. So I list a few here. So you can see that groups from either China, South Korea, and Germany are using CSM1 in very big, exciting projects. I think the bottom line is that if we look back maybe in 10, 15 years, and we can have CSM with MOM used by this wide of community, I would say that's a big success for us. And to get there, we need to resolve some challenges. First of all, how to develop the ocean grid and the scientific considerations associated with that. So we are looking at the geography and the displaced North Poles in the MOM6 grid currently we are using. And in the middle, we have deeper time, early Eocene, and then Permian Triassic. You can see that as we get deeper and deeper, we need to develop new ocean grid for paleoclimate. And that's not also true for paleoclimate. If you take the present day simulation, you run very long time in the future. If the Antarctic ice sheets start to melt, you will expose more ocean. Then the current grid may not work well, may need to be revised. next challenge, how to develop and evaluate vertical coordinates. So this is a reproduction of figures from Frank Grine. The vertical lines are the density targets in the current MOM6 setup. You can tell that it is designed to resolve the density structure of the modern ocean. And if we do paleoclimate of last glacial maximum, the cold line, and the very warm early Eocene, clearly we need to redesign the vertical coordinates to take the best advantage of the hybrid vertical coordinates. And make this even more challenging, in paleo world, people like to do transient long simulation to look at abrupt climate changes. So shown here are the AMOC in simulation and in proxy data and the temperature over the Greenland. You see that a big change in ocean circulation and the regional temperatures. So how do we design the vertical coordinates for those type of abrupt climate change? With that, I will quickly summarize. CSM3 LGM simulations show realistic glacial temperatures supporting its climate sensitivity. This is great news for us. And the model simulates shallower AMOC, agreeing well with proxy data and theory. And we do see some dependence on choices or details of MOM6 vertical coordinates over deep water formation region. And for successful paleoclimate application of CESM MOM6, we would like to learn from oceanographers about tools and scientific considerations for grid and vertical coordinates development and evaluation. And I don't have time to mention that, but the final point is that we run long simulation, equilibrium climate. So in that regard, a coarser resolution with a faster throughput would be very useful for the community. With that, I will stop here and thank you for your attention.
Questions in the room or online?
Yes, Bob, sorry, I didn't see you. So with the target densities being inappropriate, one of the big changes in the last glacial maximum is that the ocean had less volume and was saltier. Is that the thing that's driving it? Right? It needs to get denser. If the ocean as a whole is saltier, that would make everything denser on average.
Yeah,
If we were to simply rescale all of the denser coordinate surfaces by the volume mean ocean salinity, would that come close to getting us where we need to be?
I don't know. I mean, it's not just that the density shifts, the stratification changes too. And so what I'm going to talk about tomorrow is based on the stratification. But what I'm going to talk about tomorrow is not necessarily the right answer. Maybe there's a simpler thing you could do. I mean, what, Frank, you created a grid by shifting density classes or something like this? No?
I did it. The first one I gave it to Jean was basically this, and then I shifted, so it's kind of above. So shifted should be like on the blue behind us.
But yeah, I mean, like at the LGM, we have this big salinity shift, but then also one of the classical stories is of stronger salinity stratification in the lower cell of the Atlantic overturning, for instance. So yeah,
More than just the mean.
yeah, right.
If I can add, I think we want to pay special attention to the deep water formation region, because that's where we see the biggest sensitivity maybe.
I mean, the other answer, and this is not one you're going to be happy hearing, you can add extra layers that you're not using in the current state, as many as you want. It just runs contrary to your desire to make the whole thing faster. But you can have massless layers there sitting around waiting to be used, and it won't change the solution.
Will that slow down the model?
Yes, but I warned you about that.
You can change the density definitions in time, right? Probably, the Ale has no problem with that.
Ale doesn't have any problem with that.
So you could just say the densest water at the surface is always the rightmost one and then stretch the rest in between.
In principle, yeah.
The end. And this is where the surface is
Yeah,
but
but
eventually the densest in the ocean.
it's not just giving the interfaces, it's also, is the way HiCommon works, and we'll learn more tomorrow. It's always finding the cheapest interface between what is given by delta rho versus what you gave as DZ. So you might give interfaces that it might end up not being used because of your given delta Z in the HiCommon grid.
I mean, is there a fundamental reason that that needs to slow down the computation, or is there some way of being smart and saying, okay, we're clearly not using these? Is there a software solution to that?
Having massless layers that you simply don't do anything.
Yeah.
Maybe you could figure out which processors aren't using it and maybe, I mean, the code isn't written that way. The challenge is anytime you put in logic to turn things off, there's a little bit of cost there just from doing the extra logic. It's entirely possible that somebody could do it. It would certainly have an impact on the memory footprint, because if the layers are there as massless layers, they have to be there. Might work really well. I don't know.
I don't know if we need.
We haven't
to
really
do that.
tried.
So it does, we've got pretty decent results already with, that you showed today without having to add extra layers, so to speak, and slow the whole thing down. Hopefully we won't have to go that way.
Of the configurations that you showed, do you know like where overflows occur in these kind of regimes? Like right when we tune the present day API control, like we go Dynamar straight, we go. You kind of have an idea of where to look for, like, do you have an idea where to look for in these configurations?
I think based on the model results here, before the formation is pushed to the GNC for and the LVM conditions and the open ocean over the subpolar North Atlantic, I think we need to pay special attention to the overflow from GNC.
So it's similar to, well,
That's a great question, because when I was tuning the February 20th grid that you showed results, I was focusing specifically on Greenland, Scotland Ridge. Yeah, I'm glad to hear that's the right place. In the back, Dave.
Yeah, so this figure I wanted to ask about, you didn't really show the sea ice results, but like I'm fascinated with this big difference north of Alaska. Like what's going on there in the Beaufort Sea?
Yeah, at high latitudes, earlier today, someone was pointing out that in the current climate, the Arctic is just Z-star. And in the Antarctic margins too, it's mostly just Z-star, but then what'll happen is it's Z-star, 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 and then at some point it switches to isopycnal, and you usually get a big layer there. A big layer, and then that can have, a big effect on mixed layer depth. So that's kind of a hard part to tune with the current ICON 1 core.
So this may also be one where trying EPBL might work, because EPBL is not pegged to the depth of interfaces for the diagnosed turbulent mixed layer depth. If it matters. On the other hand, if it's really weakly stratified, yeah, the mixed layer may change by a lot, but doesn't have any.
Right, physical. If it's the 0.03 criterion, weakly stratified, it can have a huge. Go ahead.
One other question, and this might be kind of a last one. So MODM 6 can do wetting and drying. There was an awful lot of wetting at the end of the last glacial maximum. Wouldn't that be fun?
Just watch it creep up the coasts.
Yeah, or break Lake Agassiz and not quite so creepy.
The nice thing about the new version of CSN is that the mapping files are done on the fly. So if if that idea moves forward, like we could have the coupler C regenerating mapping files when the topography changes. Less manual intervention.
That could be really fun.
Absolutely.
Historically, you should say most of the mapping files are automatic.
Except of runoff, yeah, not all.
And Jen, are you running with live land ice now or no?
Not yet.
Yeah.
Our next step.
Yeah, that was actually, there were a lot of requests for that, coupling six ice sheets in the survey. That was one of the things that a lot of people mentioned.
Who had a question? Yeah, I just wonder where is the sea ice edge on this simulation, whether Jinsei, how much Jinsei and Lapse is covered by sea ice?
Sorry, I don't have a plot. I think it's totally covered with
Okay.
GNC.
It's common in most of the models.
Yeah. I can send you a plot afterwards.
But then I'll follow on from who, I mean, your one idea between some of the runs that have the shallower overturning were CCSM3 and CESM3. And I mean, I'd be interested in looking at the sea ice in those runs, comparing to the other ones, you know. I mean, I have a good sense of what the sea ice was doing in the pre-industrial runs, but I don't really know what's going on in these last glacial maximum runs.
Yeah, we can take a look together.
Yeah.
Anyone else? I can't see. Is there anyone online hand raised? Nope. All right. I think let's thank Sean and everyone.